more we probe the cosmos, the deeper the mystery grows. And with every answer we uncover, countless new questions emerge, some of which may never be fully resolved. Yet among them, one question has relentlessly haunted the minds of scientists for generations. How did the universe bring itself into existence? Did it emerge from an absolute void, as some theories suggest? Or was there a force beyond human comprehension that ignited the spark of creation? Or perhaps the universe has no beginning or end, existing instead in an eternal cycle of birth, expansion, and eventual destruction. From the mind-expanding concept of the Big Bang to the tantalizing possibility of a multiverse, the quest to understand the origin of reality itself continues to challenge and inspire. The Big Bang Theory stands as the most widely accepted explanation of how the universe came into being and how it has expanded ever since. According to this model, the universe began as an extraordinarily hot and dense singular point, a concentration of all matter and energy, and has been expanding ever outward through time. Various refinements of the Big Bang model help explain some of the most fundamental cosmic mysteries: why lightweight elements such as hydrogen and helium dominate the universe, why a faint residual glow of radiation, known as the cosmic microwave background, permeates space, and how galaxies and massive cosmic structures coalesced over billions of years. Central to this theory is the concept of cosmic inflation, a brief but staggering burst of expansion that occurred in the first fractions of a second after the universe began. During this period, the universe swelled exponentially, smoothing out irregularities and laying the groundwork for the vast uniformity observed in the cosmos today. The evidence supporting the Big Bang is extensive, ranging from the distribution of light elements to the precise patterns of cosmic microwave background radiation. By tracing the expansion backward, using well-established laws of physics, scientists have determined that the universe began approximately 13,787,000,000 years ago, a figure regarded as the age of the cosmos itself. During its infancy, the universe was unimaginably hot and dense, a seething primordial soup of energy and subatomic particles. As it expanded, it cooled, allowing these particles to combine into the first simple atoms, primarily hydrogen with traces of helium and lithium. Gravity, aided by the mysterious influence of dark matter, gradually pulled these atoms together, forming clouds of gas that eventually ignited to become the first stars and galaxies. Observations of distant exploding stars, or supernova, have revealed that not only is the universe expanding, but its expansion is accelerating, driven by an enigmatic force dubbed dark energy, whose true nature remains elusive. The idea of an expanding universe was first mathematically described by Russian physicist Alexander Friedmann in 1922 through the equations now known as the Friedmann equations. Shortly afterward, in 1929, American astronomer Edwin Hubble provided observational confirmation by showing that galaxies move away from Earth, with more distant galaxies receding faster, a relationship now called Hubble's law. Around the same period, Belgian physicist Georges Lemaître proposed that the universe originated from an extremely small, dense point he termed the primeval atom, laying the foundation for modern Big Bang theory. A pivotal moment came in 1964 with the discovery of cosmic microwave background radiation, the faint afterglow of the early universe. This radiation matched predictions from Big Bang models so precisely that it decisively discredited competing theories, including the steady-state model, which had argued that the universe had no beginning. Despite its explanatory power, the Big Bang theory leaves profound questions unresolved. Scientists grapple with why the universe contains far more matter than antimatter, a puzzle known as baryon asymmetry. They seek to understand dark matter, the invisible substance that exerts gravitational influence yet emits no light, and they remain mystified by dark energy, the driving force accelerating cosmic expansion. The theory relies on three key principles: the universality of physical laws, the cosmological principle asserting that the universe is uniform on large scales, and the concept of matter behaving as a perfect fluid, flowing without resistance and with pressure dependent on density. These assumptions have been rigorously tested. Measurements of the fine structure constant, which governs the interaction between light and matter, show negligible change over cosmic history. Observations of the cosmic microwave background reveal extraordinary uniformity, varying by only 1 part in 100,000. By 1995, studies confirmed that on the grandest scales, the universe is remarkably uniform, with deviations from perfect smoothness at most about 10%. These principles allow the equations of general relativity to be simplified, yielding the Friedmann-Lemaitre-Robertson-Walker metric, which models the universe's expansion and geometry. Within this framework, a critical parameter called mass energy density dictates both the universe's shape and its rate of expansion. One of the most astonishing discoveries in modern cosmology is the composition of the universe. Visible matter, the stars, planets, and luminous structures we can detect, accounts for less than 5% of the total. About 27% consists of dark matter, an invisible substance shaping galaxies through its gravitational pull, while roughly 68% is dark energy, a force propelling the accelerating expansion of space. The study of cosmic horizons, limits imposed by the finite speed of light and the universe's finite age, reveals that some regions remain forever beyond observation, while distant parts of the cosmos may ultimately remain unreachable due to the ever-accelerating expansion. In its earliest moments, the universe was an intense furnace, densely packed and searingly hot. Over billions of years, it expanded, cooled, and evolved into the intricate, expansive cosmos observed today. A vast tapestry of galaxies, stars, and planets, governed by forces both familiar and profoundly mysterious. Every new discovery peels back a layer of the universe's history, yet also unveils new enigmas, reminding us that the story of creation is far from complete, and the pursuit of understanding continues to stretch the boundaries of human curiosity. However, the precise moment when everything began, the very instant of the Big Bang itself, remains one of the deepest mysteries confronting modern physics, a puzzle that defies complete explanation even with our most advanced theories. If we attempt to rewind time using Einstein's general theory of relativity, we are led to a point where the universe compresses into a state so dense and hot that the familiar laws of physics, as we know them, simply collapse. This extreme state, known as a gravitational singularity, implies that the universe may have once possessed infinite temperature and density. Yet, the true meaning of this is elusive because general relativity alone cannot account for the unfathomable extremes present at the Big Bang. Scientists theorize that during these earliest, most ephemeral moments, the effects of quantum gravity, a mysterious and still largely unknown branch of physics that seeks to unify quantum mechanics with gravitational forces, would have dominated the universe. This enigmatic period is referred to as the Planck epoch, occurring within a fraction of a second after the universe came into existence. Specifically, it transpired in the first 100 quintillionth of a second, about 10 to the power of negative 43 seconds. At this instant, the universe was unimaginably tiny, with a characteristic length of roughly 1.66 times 10 to the power of negative 35 meters, and a temperature soaring around 100 undil 10 to the power of 32 Kelvin. The conditions were so extreme that even the fundamental particles we now recognize did not yet exist. Physicists continue their search for a coherent theory of quantum gravity to fully illuminate this fleeting, enigmatic era. As the universe expanded and cooled, the first transformative event occurred at 100 billion trillion trillionths of a second, 10 to the power of negative 37 seconds. At this juncture, the cosmos experienced an extraordinary phenomenon, a sudden and colossal expansion known as cosmic inflation. In an incredibly brief interval, the universe ballooned exponentially, far surpassing the speed of light. This rapid stretching smoothed the fabric of space and drastically lowered the universe's temperature by a factor of 100,000. The process also amplified tiny quantum fluctuations, setting the foundation for the formation of galaxies and cosmic structures that would emerge billions of years later. Soon after, at around 1/1,000,000th of a second, 10 to the power of negative 36 seconds, another pivotal event unfolded. One of the four fundamental forces, the strong nuclear force, diverged from the others, leaving the electromagnetic and weak nuclear forces still united. This era, called the electroweak epoch, laid the groundwork for subsequent cosmic transformations. By the time the universe reached 100 billion trillion trillionths of a second, between 10 to the power of negative 33 and 10 to the power of negative 32 seconds, cosmic inflation had concluded. The observable universe had expanded to a volume larger by an almost incomprehensible factor of 1, followed by 78 zeros. Following this expansion, the universe entered a phase known as reheating, where the energy generated by inflation transformed into matter and radiation. Temperatures rose high enough to create a dense, searing plasma of quarks and gluons, the fundamental building blocks of atoms, moving freely in an intensely energetic environment. During this period, particles and their antimatter counterparts collided and annihilated continuously. Yet a subtle imbalance called baryogenesis allowed a minute fraction of matter to survive. For every 30 million pairs of matter and antimatter particles, a single extra particle of matter endured. This tiny excess ultimately became the galaxies, stars, planets, and all structures that define our universe today. As the universe continued its relentless expansion, it cooled, causing particle energies to decrease and fundamental forces to settle into their current forms. A crucial event in this process was the separation of the electromagnetic force from the weak nuclear force, which occurred in an extraordinarily brief moment, about 1 trillionth of a second after the Big Bang. By approximately 100 billionths of a second, the energy levels had fallen to values that modern particle accelerators can now probe. When the universe was just a millionth of a second old, quarks and gluons began to coalesce into larger composite particles called baryons, including protons and neutrons, the essential constituents of atomic nuclei. Because of the slight predominance of quarks over their antimatter counterparts, antiquarks, matter began to dominate. As the universe cooled further, new pairs of protons and antiprotons, and neutrons and antineutrons could no longer form, triggering a massive annihilation of antimatter. Only roughly one matter particle out of every 100 million survived. A similar annihilation occurred about 1 second after the Big Bang, when electrons and positrons collided, leaving a universe dominated by protons, neutrons, and electrons. Most of the remaining energy was carried by photons, with a smaller contribution from elusive neutrinos. Minutes after the Big Bang, when temperatures had dropped to about 1 billion degrees Kelvin, protons and neutrons began combining to form the first atomic nuclei, primarily deuterium and helium. This process, known as Big Bang nucleosynthesis, established the primordial elemental makeup that would later coalesce into stars, planets, and all the complex matter in the universe. The early universe, though now faintly understood, remains a testament to the astonishing complexity and profound mystery of cosmic origins, with each fraction of a second holding clues to how everything around us came to exist. However, most of the protons never fused into heavier elements and instead remained as simple hydrogen nuclei, a basic building block that would go on to become the most abundant element in the cosmos. As the universe continued to age, matter gradually took center stage in shaping the vast structures we observe today. Roughly 50,000 years after the Big Bang, the pull of gravity from matter began to outweigh the pressure from radiation, marking a subtle but crucial turning point in cosmic evolution. Then, approximately 380,000 years after the universe's fiery birth, conditions had cooled enough for electrons to settle into orbit around atomic nuclei, forming neutral atoms, primarily hydrogen. This epoch, known as recombination, was monumental because it allowed light to travel unimpeded through space for the very first time, creating a transparent universe. The faint afterglow of this ancient light remains detectable even now, seen as the cosmic microwave background radiation, a relic whisper from the dawn of time. Following recombination, minute differences in density across the cosmic landscape led to regions that drew in more matter than their surroundings, gradually forming colossal clouds of gas. Over the course of millions of years, these clouds succumbed to gravity, collapsing to ignite the first stars and eventually coalescing into galaxies and the enormous cosmic web we see stretching across the universe today. The precise nature of matter has been a key factor in these formations. Scientists categorize it into 4 primary types: cold dark matter, warm dark matter, hot dark matter, and baryonic matter. the ordinary matter that makes up planets, stars, and living beings. Measurements from the Wilkinson Microwave Anisotropy Probe, known as WMAP, suggest a universe dominated by cold dark matter. According to these observations, dark matter constitutes roughly 23% of the universe's total matter and energy, while baryonic matter accounts for just under 5%. The remaining 73% is thought to be dark energy, a mysterious and invisible force accelerating the expansion of the cosmos. Evidence for dark energy comes from multiple avenues. Observations of exploding stars known as Type 1a supernova and the faint remnant glow from the early universe, the cosmic microwave background, both point to a universe largely governed by this elusive energy. Dark energy appears to pervade all of space, its presence subtle yet overwhelmingly dominant, shaping the fate of the cosmos. In the universe's infancy, dark energy existed but was overshadowed by the intense density of matter, which exerted a powerful gravitational brake, slowing expansion. As billions of years passed and matter grew increasingly diffuse, dark energy began to dominate, flipping the cosmic switch so that expansion accelerated rather than decelerated. Scientists attempt to frame dark energy within Einstein's general relativity as a cosmological constant, a mathematical placeholder that captures its effect, yet its fundamental nature remains a profound mystery. Researchers are probing its properties through meticulous observations, theoretical modeling, and efforts to integrate it with the standard model of particle physics, which governs the known fundamental particles and forces of nature. The universe's evolution from its earliest flickers of light to the sprawling cosmic structures visible today is described by the lambda cold dark matter model, abbreviated as LCDM. This framework merges quantum mechanics, which governs the behavior of the tiniest particles, with general relativity, the theory describing space, time, and gravity on a grand scale. Yet what occurred before the universe was 1/quadrillionth of a second old, a time measured as 1 divided by 1,000 trillion seconds, remains enigmatic. No current experiment or theory fully explains this earliest instant, and understanding it stands as one of the greatest unsolved mysteries in physics. The term Big Bang itself was coined by British astronomer Fred Hoyle during a BBC radio broadcast in March 1949, and while discussing competing cosmological theories, he used the phrase to describe a model in which all matter in the universe originated in a single, enormous event in the distant past. Initially, the term did not catch on widely and only became popular in the 1970s. Many believe Hoyle intended it as a slight against the concept, since he favored the steady-state model, which posited a universe with no beginning or end. Hoyle later clarified that he did not intend mockery, merely seeking a vivid image to distinguish between the competing ideas. Historians like Helga Krag have found little evidence to suggest he was derisive. Ironically, the phrase Big Bang is somewhat misleading. It conjures images of a violent explosion emanating from a single point into surrounding emptiness, yet the reality was profoundly different. The event was not a localized blast, but the entire universe expanding from an incredibly hot, dense state. The word bang also implies a loud noise, yet sound waves cannot traverse the vacuum of space, making the metaphor all the more inaccurate. Despite the misnomer, the Big Bang remains the most compelling and extensively tested explanation for the universe's origin and its ongoing evolution, providing a narrative that stretches from the first hydrogen atoms to the cosmic web spanning billions of light years. However, despite countless attempts by scientists to find a more suitable or elegant term, no alternative ever managed to replace it. Long before the phrase Big Bang entered the popular lexicon, researchers were already making profound discoveries hinting that the universe itself was not static, that it was somehow stretching outward, expanding beyond anything previously imagined. In the year 1912, an American astronomer named Vestos Slipher undertook a painstaking study of the light coming from distant cosmic objects, then called spiral nebulae. Using a phenomenon now known as the Doppler shift, he observed that nearly all of these nebulae were moving away from Earth. At the time, however, there was considerable uncertainty about their nature. Were they distant galaxies separate from our own Milky Way, or merely objects within it? A decade later, in 1922, a Russian mathematician and physicist named Alexander Friedmann applied Albert Einstein's general relativity equations to a revolutionary concept. The universe might not be unchanging. Instead, it could be expanding or contracting. This revelation was nothing short of shocking, as even Einstein himself had been convinced that the cosmos was eternal and static. Then, in 1924, American astronomer Edwin Hubble confirmed that the spiral nebulae were in fact entire galaxies, each lying far beyond our own. Using the massive Hooker telescope, which spanned 100 inches or 2.5 meters, Hubble measured their distances with unprecedented precision. A few years later, in 1929, he made an even more astonishing observation. The farther away a galaxy was, the faster it appeared to move away from Earth. This correlation, now enshrined as Hubble's law, became the first compelling evidence that the universe was indeed expanding. At nearly the same time, in 1927, a Belgian physicist and Catholic priest named Georges Lemaitre independently arrived at the conclusion that the universe was expanding. He even anticipated the relationship between distance and velocity that Hubble would later confirm observationally. Yet, Lemaitre did not stop there. In 1931, he proposed that if the universe is expanding today, there must have been an earlier moment when all matter was compressed into a single unimaginably dense and minuscule point, which he called the primeval atom. This daring notion laid the foundation for what would eventually become the Big Bang theory. During the 1920s and 1930s, many scientists were uncomfortable with the idea that the universe had a beginning. The prevailing belief held that the cosmos was eternal, infinite, and uncreated. Some scholars even avoided discussing a beginning altogether, wary of echoing religious creation narratives. The eminent British astrophysicist Arthur Eddington openly rejected the notion, calling it repugnant because it implied that matter had not always existed. Many others supported the steady state theory, which suggested that new matter continuously emerged as the universe expanded, maintaining a constant appearance over time. Alternative theories also proliferated. Some scientists imagined a cyclical universe, oscillating between expansion and contraction, while others, like Fritz Zwicky, proposed hypotheses such as tired light, in which photons lost energy over time, making distant galaxies appear to recede. After the Second World War, two major competing frameworks came to dominate cosmology. On one side stood Fred Hoyle, an ardent supporter of the steady-state theory, maintaining that the universe was eternal and self-sustaining. On the other side were proponents of the expanding universe model, championed by Lemaitre, among them George Gamow, who, with colleagues Ralph Alpher and Robert Herman, developed theoretical models describing how light elements like hydrogen and helium could have formed in the early universe. They predicted that if the universe had once been incredibly hot and dense, remnants of that primordial heat should still linger as a faint, omnipresent glow, what we now call cosmic microwave background radiation. The debate persisted for decades, but accumulating evidence gradually tipped the scales. The decisive breakthrough came in 1964 when scientists Arno Penzias and Robert Wilson accidentally detected the cosmic microwave background radiation. This faint energy, uniformly spread across the sky, matched precisely what the Big Bang theory had predicted, serving as a cosmic fingerprint of the universe's fiery birth. Slowly, the once controversial idea of the universe having a beginning became widely accepted, transitioning from theoretical speculation to scientific consensus. Ironically, the term Big Bang itself was coined by someone who never believed in the theory. In March of 1949, British astronomer Fred Hoyle, an advocate of the steady-state model, used the phrase on a BBC radio broadcast, intending it dismissively. Yet the term resonated, capturing the public imagination, and stuck as the popular name for Lemaitre's revolutionary concept. For years, the scientific community remained divided, but as radio wave observations accumulated, the evidence increasingly favored the Big Bang. In the late 1960s and early 1970s, visionary physicists such as Roger Penrose, Stephen Hawking, and George Ellis published pioneering studies demonstrating that, based on Einstein's equations, the universe must have originated from a singularity, a point of infinite density and energy. Over the next 2 decades, cosmologists refined the Big Bang model, tackling unresolved mysteries about the cosmos. In 1981, physicist Alan Guth introduced the concept of cosmic inflation, a period of extraordinarily rapid expansion in the universe's earliest moments, which elegantly resolved questions about its uniformity and structure. Debates raged over the precise value of the Hubble constant, which quantifies the expansion rate of the universe, and the total amount of matter thought to dictate the cosmos's ultimate fate. At that time, dark energy remained unknown, an unseen force that would later reshape our understanding of cosmic acceleration. Since the late 1990s, breakthroughs in observational technology, space-based observatories like COBE, WMAP, and the Hubble Space Telescope have delivered remarkably precise data, revealing astonishing truths. Among these, perhaps the most profound realization was that the universe's expansion is not slowing down, as once believed, but accelerating, driven by the enigmatic force of dark energy. Today, the Big Bang Theory stands as the most comprehensive and compelling explanation for the origin and evolution of the universe. It illuminates the origins of light elements such as hydrogen and helium, explains the presence of the cosmic microwave background, clarifies the large-scale distribution of galaxies, and accounts for their observed recession as articulated by Hubble's law. These observations, often described as the 4 pillars of the Big Bang model, form a coherent framework demonstrating that the universe began from a singular, incredibly dense point and has been expanding ever since, continuing to evolve in ways that inspire wonder and scientific inquiry. One of the earliest signs pointing to the validity of the Big Bang Theory emerged from the realization that galaxies are receding from us, a motion revealed through the stretching of their light into longer, redder wavelengths, a phenomenon known as redshift. Observing this cosmic redshift gave scientists the first tangible evidence that the universe is expanding, hinting at a dramatic origin in the distant past. Following this discovery, astronomers made another groundbreaking observation: the detection of the cosmic microwave background, a faint, omnipresent radiation that pervades all of space. This signal is a remnant of the universe's earliest moments, a faint echo from a time when the cosmos was dense, hot, and opaque. In addition to redshift and the cosmic microwave background, researchers confirmed that the proportions of light elements in the universe correspond with predictions from Big Bang nucleosynthesis, a process describing how hydrogen, helium, and traces of other light elements formed in the first few minutes after the Big Bang. Helium-4, for instance, is expected to constitute about a quarter of the universe's total mass of hydrogen, deuterium about 1,000th, helium-3 roughly 110,000th, and lithium-7 only 1 billionth of hydrogen's mass. Observational measurements largely align with these predictions, particularly for deuterium, while minor discrepancies like the cosmological lithium problem continue to puzzle scientists. Modern astronomy has added further layers of evidence. By examining how galaxies form, evolve, and cluster together into colossal cosmic structures, researchers have painted a picture that consistently fits Big Bang predictions. The emergence of the first galaxies and quasars occurred within roughly 1 billion years after the Big Bang, with subsequent generations of stars and galaxies evolving over billions of years. Observing extremely distant galaxies allows scientists to witness the universe as it existed billions of years ago, revealing marked differences from galaxies closer to us, which represent later stages of cosmic evolution. These observations directly contradict the old steady-state theory, which posited an eternal, unchanging universe, and instead confirm a dynamic cosmos that has grown and evolved over time. To explain the universe's ongoing expansion and its large-scale behavior, scientists have proposed the existence of dark matter and dark energy. Dark matter, which cannot be observed directly, appears to constitute the majority of the universe's mass. Its presence is inferred from its gravitational effects on galaxies and galactic clusters, and numerous experiments aim to uncover its true nature. Dark energy, conversely, is thought to drive the accelerating expansion of the universe, though its fundamental properties remain a profound mystery. Other puzzling cosmic behaviors, such as the uneven distribution of dark matter in galactic centers and the unusual behavior of small galaxies, continue to challenge researchers. The relationship between distance and recession speed, known as Hubble's law, quantifies the expanding universe. Galaxies farther away move away faster, a concept first predicted in the 1920s by Alexander Friedman and Georges Lemaitre and observationally confirmed in 1929 by Edwin Hubble. Yet, a modern puzzle called the Hubble tension arises from differing expansion rates derived from the cosmic microwave background versus measurements of galaxy distances, leaving scientists searching for a resolution. The accidental discovery of the cosmic microwave background in 1964 by Arno Penzias and Robert Wilson provided one of the most decisive confirmations of the Big Bang. While working with a radio antenna, they detected a mysterious, uniform background noise that emanated from all directions in space. This faint afterglow, a relic of the universe's hot, dense infancy, matched prior theoretical predictions and earned them the Nobel Prize in Physics in 1978. The cosmic microwave background originates from around 372,000 years after the Big Bang, when charged particles combined into neutral atoms, allowing light to travel freely for the first time and leaving the universe transparent. Subsequent missions, including NASA's COBE satellite in 1989, the Boomerang balloon experiment in 2001, the Wilkinson microwave anisotropy probe in 2003, and the European Space Agency's Planck probe in 2009, refined these measurements. COBE confirmed the cosmic microwave background's perfect blackbody spectrum and detected tiny temperature fluctuations, which seeded the formation of galaxies and stars. Boomerang and subsequent probes revealed the universe's near-flat geometry and offered highly precise measurements of key cosmic parameters, deepening our understanding of the universe's birth and evolution. The formation of light elements, galaxy structures, and cosmic clusters continues to align with Big Bang predictions. Scientists can predict the abundances of helium-4, helium-3, deuterium, and lithium-7 using the photon-to-baryon ratio, which can also be inferred from tiny fluctuations in the cosmic microwave background. Observed element ratios mostly match these predictions, confirming that the Big Bang remains the only known explanation for the universe's elemental composition. The patterns of star formation, the distribution of galaxies and quasars, and the emergence of cosmic structures all follow trajectories anticipated by theoretical models. Remarkable discoveries persist into the 21st century. In 2011, astronomers detected clouds of primordial gas through the light of distant quasars. Unlike previously observed cosmic objects containing heavy elements like carbon, oxygen, and silicon formed inside stars, these clouds seemed pristine, consisting of the universe's first gases. Each new observation reinforces the narrative of a universe with a clear beginning, evolving over billions of years into the vast, structured cosmos we observe today. However, these two immense clouds of gas show no trace of heavier elements, hinting that they formed mere minutes after the Big Bang during a process known as Big Bang nucleosynthesis. These primordial clouds act as living fossils, preserving the earliest moments of our universe. Scientists have pieced together the age of the cosmos through multiple independent approaches, each reinforcing the others. One method relies on measuring the universe's expansion rate using the Hubble constant alongside observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang. Another approach delves into the lifetimes of the oldest stars in globular clusters, examining the nuclear reactions and radioactive elements within them to gauge their age. Additional insights emerge from studying distant supernovae, exploding stars whose brightness and distance reveal the universe's expansion history, and from analyzing minute temperature fluctuations in the cosmic microwave background. All these diverse, cross-check measurements converge on the same estimate, strongly supporting the standard cosmological framework known as the Lambda Cold Dark Matter Model, or LCDM. Yet, not every observation fits neatly into this model. One particularly enigmatic quasar, labeled APM 08279 plus 5255, exhibits such complexity that some researchers question whether it could have formed within the time constraints imposed by the Similarly, the Big Bang theory predicts that the cosmic microwave background should have been hotter in the distant past. Observations of faraway gas clouds confirm this prediction by revealing subtle absorption patterns in their light, supporting the notion that the Sunyaev-Zeldovich effect, a distortion of cosmic background radiation by galaxy clusters, remains roughly constant across vast distances. Scientists have verified this effect, though precise measurements are complicated because galaxy clusters themselves evolve over billions of years. Looking forward, the next frontier lies in detecting ancient gravitational waves, ripples in spacetime that could carry signals from less than 1 second after the Big Bang. Success in this endeavor would open a window onto the universe's first heartbeat, offering insights into the mechanisms that sparked everything we see today. The Big Bang Theory has illuminated much about our cosmic origins, but each discovery tends to reveal deeper mysteries. Problems such as the horizon problem, the magnetic monopole problem, and the flatness problem are typically addressed by the theory of cosmic inflation, which proposes a brief period of extremely rapid expansion in the universe's infancy. Despite its explanatory power, many aspects of inflation remain uncertain, and some original proponents have questioned its validity over time. One of the universe's most perplexing mysteries is the dominance of matter over antimatter. Standard models suggest that the early universe, in its first fractions of a second, should have produced equal amounts of matter and antimatter, which would annihilate each other completely. Yet, the cosmos we observe is overwhelmingly composed of ordinary matter. To account for this imbalance, scientists proposed a process called baryogenesis, which requires 3 essential criteria, known as the Sakharov conditions: baryon number violation, the breaking of certain fundamental symmetries labeled C symmetry and CP symmetry, and departures from thermal equilibrium. While these conditions could theoretically occur within the standard model of particle physics, they are insufficient to explain the universe's observed asymmetry, leaving the question unresolved. Compounding the mystery, observations of Type 1a supernovae revealed that the universe's expansion is not slowing under the pull of gravity, but is accelerating. This startling revelation led to the hypothesis of dark energy, a mysterious form of energy believed to make up most of the universe's total energy content. Detailed studies of the cosmic microwave background indicate that the universe is nearly geometrically flat, implying that its total mass and energy must approximate a precise value called the critical density. Yet, visible and dark matter combined account for only about 30% of this density, leaving 70% attributed to dark energy. Dark energy also shapes the universe's large-scale structure, influencing phenomena like gravitational lensing, where light from distant galaxies bends around massive clusters, and baryon acoustic oscillations, patterns in the distribution of galaxies originating from sound waves in the early universe. Although dark energy explains these observations well, its true nature remains unknown, with possibilities ranging from vacuum energy to more exotic physics. Data from the Wilkinson Microwave Anisotropy Probe in 2008 painted a detailed picture of the universe's composition. Roughly 73% dark energy, 23% dark matter, 4.6% ordinary matter, and less than 1% neutrinos. As the universe continues to expand, the proportion of matter decreases, while dark energy remains nearly constant, suggesting that its influence will grow ever more dominant over cosmic time. Alongside dark energy, dark matter presents another profound mystery. Invisible yet gravitationally potent, dark matter is essential for explaining galaxy rotation curves and the formation of cosmic structures. In the 1970s and 1980s, astronomers realized that the visible matter in galaxies was insufficient to account for their gravitational behavior, implying that most matter is unseen. Estimates suggest that as much as 90% of all matter could be dark. Without it, galaxies would not hold together as observed, and the large-scale cosmic web of clusters and filaments would not have formed in its familiar pattern. The universe, in its vast complexity, is thus a delicate balance of forces and unknown components. From the first moments of nucleosynthesis to the accelerating expansion driven by dark energy, from the dominance of matter over antimatter to the hidden scaffolding of dark matter, each revelation opens new questions. Scientists continue to probe, measure, and theorize, inching closer to understanding the origins and ultimate fate of everything that exists, yet realizing that the deeper they look, the more intricate and mysterious the cosmos becomes. the amount of an element known as deuterium scattered throughout the universe is astonishingly lower than expected if we exclude the presence of dark matter. Although no scientist has ever held a dark matter particle in their hand or observed it directly under a microscope, its existence is inferred from the universe itself, whispered in the motions of galaxies as they dance within clusters, revealed in the subtle bending of light through gravitational lensing, traced in the sprawling distributions of scorching gas in galaxy clusters, and imprinted in the minute temperature variations of the cosmic microwave background that permeates space like a ghostly echo of the cosmos's infancy. Physicists have proposed a vast zoo of potential dark matter candidates, including exotic particles that evade interaction with ordinary matter except through the pull of gravity. Across continents, from deep underground laboratories to particle accelerators probing the very fabric of reality, experiments tirelessly hunt for these elusive entities. Yet despite decades of effort, none have emerged from hiding. Even as dark matter remains the most compelling framework to explain countless cosmic phenomena, the model is far from flawless. Mysteries persist, teasing the edges of our understanding. Consider the dwarf galaxy problem. Computer simulations suggest that the universe should be brimming with countless small galaxies, yet our telescopes find far fewer. Then there is the cuspy halo problem. Theory predicts that the centers of galaxies should be dense, sharp peaks of dark matter, but observations reveal gentler, smoother distributions. In response, some scientists have dared to challenge conventional thinking, proposing alternative theories that modify the laws of gravity themselves, sidestepping the need for dark matter entirely. However, no alternative has yet matched the dark matter paradigm's explanatory power across the full spectrum of cosmic observations. Beyond dark matter, the universe conceals even more confounding enigmas. Among the most notorious is the cosmological constant problem, sometimes called the most embarrassing puzzle in physics. Astronomers measure the universe's dark energy, the mysterious force driving cosmic acceleration, and find it astonishingly small compared to predictions from quantum physics. Fundamental calculations suggest that empty space should seethe with energy far beyond what telescopes detect. Why this vast discrepancy exists remains one of modern science's most profound questions. Some researchers return to Einstein's cosmological constant, a term he first introduced to stabilize the universe and later abandoned, while others explore dynamic concepts like quintessence, where dark energy evolves over time rather than remaining constant. Despite humanity's ever-expanding knowledge of the cosmos, mysteries abound. Dark matter and dark energy remain shadowy presences. The imbalance between matter and antimatter continues to defy explanation. The acceleration of cosmic expansion challenges every expectation. Each new discovery illuminates some corners of the universe, but often casts deeper shadows elsewhere, revealing questions we cannot yet imagine answering. The horizon problem exemplifies the universe's subtle perplexities. Information cannot travel faster than light, so only regions of space that have had time to interact could influence each other. The particle horizon marks the furthest distance any influence could reach. Yet, the cosmic microwave background, the faint afterglow of the early universe, appears astonishingly uniform across the sky. Regions separated by more than about 2 degrees should never have exchanged energy or heat. How then did the cosmos achieve such remarkable uniformity? The answer emerges from inflation theory, a radical vision of the universe's earliest moments. At a time when even protons and neutrons did not exist, a uniform energy field dominated all of space, driving an explosive, exponential expansion that flung regions far apart in the blink of an eye. Areas that seem impossibly distant today were once intimate neighbors, able to equilibrate temperatures before being torn asunder. Inflation carries even stranger consequences. Quantum fluctuations, tiny random blips of energy predicted by Heisenberg's uncertainty principle, were stretched to cosmic scales, forming the seeds of galaxies, stars, and the vast cosmic web we observe. Modern measurements of the cosmic microwave background confirm that these early variations were exquisitely balanced, as inflation predicted. Yet inflation raises further mysteries. Most models indicate that inflation ended long before the electroweak epoch, when fundamental forces like electromagnetism and the weak nuclear force separated. If distant regions were already cut off by that time, why do we not see massive irregularities in the cosmos today? This remains an open question, challenging even the most seasoned cosmologists. In the 1970s, grand unified theories predicted the existence of magnetic monopoles, particles that act as solitary north or south poles of a magnet. These should have been abundant in the early, high-energy universe, yet none have ever been observed. Inflation offers a compelling solution. By stretching the universe so dramatically, any monopoles that formed were diluted to near invisibility, scattered across unimaginable distances. The universe's flatness presents another subtle marvel. Space can curve like a sphere, warp like a saddle, or remain flat like a sheet of paper, depending on its total energy density. If the early universe had been even slightly off balance, it would have collapsed into oblivion or expanded into near nothingness. Yet billions of years later, the cosmos appears astonishingly flat. To achieve this, the density of the universe at the time of nucleosynthesis, mere minutes after the Big Bang when the first atomic nuclei coalesced, had to be precise within 1 part in 10 quadrillion. Such perfection seems impossible without an active mechanism, and inflation provides that mechanism. Just as a rapidly inflating balloon smooths wrinkles on its surface, the exponential stretching of space drove the universe toward flatness, ensuring the cosmos we inhabit remains balanced across unimaginable scales. Many people mistakenly believe the Big Bang Theory explains how everything, including time, space, and energy, came into existence. But in reality, it is a framework for understanding the evolution of the universe from a hot, dense state. The deeper truths lie in the cosmic puzzles that continue to elude us, revealing a universe more mysterious, more intricate, and more awe-inspiring than our ancestors could ever have imagined. However, that is not quite true. The Big Bang Theory does not answer the ultimate question of why the universe exists. It does not reveal the cause of existence itself, but it provides a detailed narrative of how the universe we inhabit emerged from an extraordinarily small, unimaginably hot, and incredibly dense state. Many people mistakenly picture the Big Bang as a tiny object that suddenly bursts outward like a balloon being inflated. In truth, when scientists discuss the size of the universe at the time of the Big Bang, they are referring solely to the observable universe, the portion of the cosmos we are capable of seeing. The entire universe could be vastly larger than this, perhaps even infinite, and its true scale may forever elude our understanding. Another widespread misconception is imagining the Big Bang as a violent explosion, with matter flying outward like shrapnel from a bomb. Reality was far subtler, yet far more profound. Space itself expanded, stretching like a cosmic fabric carrying galaxies along in its flow. Scientists often describe this phenomenon as the expansion of space, while others explain it as galaxies moving away from each other. Both perspectives are valid. They simply focus on different aspects of the same cosmic process. Hubble's law quantifies this expansion. The farther a galaxy is from us, the faster it appears to be receding. Some galaxies seem to move faster than light, yet this does not violate the laws of physics. Instead, it reflects the expansion of space itself, increasing distances between galaxies at a rate that can exceed the speed of light without contravening any physical principles. This cosmic stretching is intricately linked to the redshift observed in distant galaxies. While it is partly accurate to say this redshift arises from space expanding, the phenomenon is most directly understood through the Doppler effect, the same principle that makes an ambulance siren change pitch as it passes by. In the case of light traveling across the cosmos, the wavelengths stretch, shifting toward the red end of the spectrum. By measuring this redshift, scientists can infer the rate at which the universe is expanding and even reconstruct a timeline stretching back to its earliest moments. Despite the profound insights provided by the Big Bang Theory, there are limits to what we can predict. Our models can extend far beyond the current age of the universe, yet even then, the ultimate fate of the cosmos remains uncertain. Equally mysterious is the origin of the universe itself. In its earliest moments, the cosmos was unimaginably hot and dense. Belgian physicist Georges Lemaitre referred to this primordial state as the primeval atom, while another scientist, George Gamow, used the term elim to describe the dense primordial matter from which all things emerged. How this initial state came into existence remains unknown. What the Big Bang theory does accomplish is tracing the universe's evolution after its initial state. Scientists have proposed that the stability of the universe may be linked to the fundamental laws of physics, and some speculative models suggest the possibility of an infinite number of universes, only some of which possess the right conditions for life. The question of what came before the Big Bang, however, remains one of the most profound mysteries in physics. Einstein's theory of general relativity underpins our understanding of the early universe, but it breaks down at extremely high energies. To truly comprehend the first fractions of a second, a unified theory of quantum gravity, one that reconciles gravity with quantum mechanics, is needed. Some theories even suggest that time itself may have no meaning prior to the Big Bang, making the question of a before meaningless. Among the speculative ideas, the quantum fluctuation model proposes that the Big Bang originated from a sudden but random fluctuation in a quantum field. While seemingly improbable in an infinite temporal framework, even the most unlikely events eventually occur. Other models explore the concept of an emergent universe, in which the cosmos existed eternally in a low-energy state before transitioning into an expansionary phase, echoing ancient myths of the universe emerging from a cosmic egg. The no-boundary model, formulated by Stephen Hawking and James Hartle, posits that the universe may not have had a beginning in the conventional sense. Instead, space and time emerge smoothly from a finite past. In string theory-based brain cosmology, our universe could exist on a higher dimensional membrane, with the Big Bang resulting from a collision with another such membrane. Cyclic universe models suggest an endless cycle of expansion and contraction, with the Big Bang representing the rebirth of a previous collapsing universe. Eternal inflation and the multiverse hypothesis propose that different regions of space expand at varying rates, forming countless bubble universes, with ours being just one among an uncountable multitude. Despite remarkable progress in understanding the Big Bang, countless questions remain unanswered. Future advances in quantum physics, cosmology, and gravitational theory may one day illuminate what transpired in those first incomprehensible moments or even before. Until then, the story of the universe remains among the greatest mysteries ever contemplated. Before the discovery of dark energy, scientists considered two primary scenarios for the ultimate fate of the universe. In the first scenario, if the universe contained excessive mass, gravity would eventually halt its expansion, reversing the process and drawing all matter inward. Over billions of years, the cosmos would stop growing, contract, and heat up, culminating in a colossal collapse known as the Big Crunch, compressing the universe into a state resembling its fiery origin. In the second scenario, if the universe possessed just enough mass, or less, it would continue expanding indefinitely, though at a gradually slowing pace. Over time, stars would exhaust their available fuel, preventing new stars from forming. The remaining stars would ultimately burn out, leaving behind cold remnants such as white dwarfs, neutron stars, and black holes. Collisions and mergers between these remnants would produce ever larger black holes. Meanwhile, the universe would cool toward absolute zero in a gradual process called the Big Freeze. If protons, the fundamental building blocks of matter, are unstable, all ordinary matter would eventually decay, leaving only radiation and black holes. Even black holes would eventually evaporate through Hawking radiation, leading to a state known as heat death, in which all usable energy is gone and no physical processes could occur. The Big Bang, its origins, evolution, and eventual fate continue to challenge human understanding, presenting a cosmic narrative of incomprehensible scale, stretching from the birth of space and time to the potential silence of the ultimate heat death. It is a story of infinite possibility, staggering complexity, and profound mystery, beckoning us to explore ever deeper into the universe's hidden truths. However, modern discoveries reveal that the universe is not merely expanding. It is accelerating in its expansion at an ever-increasing rate, driven by a mysterious and enigmatic force known as dark energy. This means that over the course of unimaginable eons, an ever-growing number of galaxies will drift so far from our own that we will never again be able to see them, communicate with them, or interact with their contents. The ultimate fate of this vast cosmic tapestry remains uncertain. Yet one of the most widely accepted frameworks, the lambda cold dark matter model, proposes a future in which galaxies, stars, and other structures held together by gravity will remain intact while the vast spaces between them grow colder, darker, and increasingly isolated. Over time, this slow but relentless expansion could lead to what physicists call the heat death of the universe, a state of maximum entropy where all motion ceases and energy becomes evenly dispersed. But there exists an even more dramatic possibility known as the Big Rip. Should dark energy grow stronger over time, it could, in theory, begin to pull apart the very fabric of existence. Galaxies would disassemble, stars would crumble, planets would shatter, atoms would be torn apart, and even the tiniest components of matter could be ripped from one another. In such a scenario, the universe would not merely fade quietly into stillness, it would be destroyed in a violent, all-encompassing unraveling, leaving nothing intact. Beyond the domain of physics, the origin of the universe, the Big Bang, has inspired profound debates in philosophy and religion. Some interpret it as compelling evidence of a divine creator orchestrating the cosmos, while others argue that it renders a divine presence unnecessary, positing that the universe arose from natural laws alone. These discussions place the Big Bang at one of the most fascinating crossroads of human thought, where science, spirituality, and philosophical inquiry intersect. When humans attempt to imagine the universe's beginnings, the mind often conjures a vast, empty void preceding existence itself. Yet modern physics paints a far more intricate picture. Space, far from being a simple vacuum of nothingness, is in fact an invisible, vibrant arena teeming with energy and subtle activity. This is the realm of quantum mechanics, the branch of physics that probes the behaviors of reality at its most minute scales. At the heart of quantum mechanics lies a revelation that is both counterintuitive and extraordinary. Even when stripped of all matter and light, space is never truly empty. Instead, it seethes with quantum fluctuations, transient bursts of energy that emerge and vanish in mere instants. These fluctuations are not random chaos, but fundamental features of the universe, potentially holding the key to answering the most profound question of all: how did the universe begin? For millennia, humans assumed that removing every particle, every atom, and every photon from a region of space would leave behind true nothingness. This concept of a void was a cornerstone of both scientific and philosophical thought. Yet, advances in quantum physics over the past century have upended this assumption entirely. The emptiness we perceive is actually a roiling sea of energy, constantly shifting under the influence of quantum fluctuations. These fluctuations arise from the uncertainty principle formulated by the physicist Werner Heisenberg, which states that at the deepest level of reality, it is impossible to know both the position and momentum of a particle simultaneously with perfect precision. This fundamental unpredictability means that even in a vacuum, energy is never truly still. The result is a strange, restless foam of energy, known as quantum foam, existing at the tiniest scales of reality. Though invisible to the naked eye, its presence has been measured and experimentally confirmed. One of the first landmark confirmations came in 1947 through the work of Dutch physicists Hendrik Casimir and Dirk Polder. In a deceptively simple yet revolutionary experiment, they positioned two small flat metal plates extremely close together in a vacuum. Classical physics predicted no interaction, yet the plates inexplicably moved toward one another, drawn together by an unseen force. This phenomenon, now called the Casimir effect, revealed that even a vacuum is alive with energy. The restricted quantum fluctuations between the plates created a pressure imbalance, pushing them together. This experiment shattered the notion of emptiness and confirmed the tangible effects of quantum fluctuations. If empty space is suffused with such energy, could these fluctuations have been the spark that birthed the universe itself? Many physicists believe they could have. According to leading cosmological theories, the universe may have emerged from a quantum fluctuation in a primordial vacuum, a seething field of latent energy waiting for the right conditions. In this view, the Big Bang was not a creation from absolute nothingness, but an expansion from a pre-existing energetic state. Quantum field theory and the theory of cosmic inflation support this, suggesting that in the earliest moments, the universe underwent a staggeringly rapid expansion, transforming a tiny, unstable fluctuation into the vast cosmos we observe today. Even after the Big Bang, quantum fluctuations continued to shape the universe. In those first unimaginable moments, the universe was a seething, incandescent maelstrom of energy. Minute fluctuations acted as seeds, tiny variations in density that would eventually grow into the vast cosmic structures of galaxies, stars, and clusters. What began as almost imperceptible ripples in energy became the scaffolding for the cosmic web, the intricate lattice of matter spanning billions of light years. The universe, it seems, emerged not from a perfect void, but from a dynamic, restless sea of energy. And this restless nature continues to influence its evolution to this day. However, as the universe expanded, the tiniest irregularities in energy began to disperse across unimaginable distances. Over billions of years, these almost imperceptible differences in energy and density were gradually amplified by the relentless pull of gravity. What once was a nearly uniform expanse slowly transformed, each microscopic fluctuation acting as a seed from which galaxies, stars, and planets eventually emerged. Without these initial irregularities, the cosmos might have remained a smooth, lifeless void, and the intricate tapestry of life we witness today may never have come into existence. The theory of cosmic inflation, first proposed by physicist Alan Guth, provides a profound explanation for how these quantum fluctuations were stretched to colossal proportions in the early universe. During this extraordinary epoch, the universe expanded at an unimaginable speed, turning microscopic, fleeting differences in energy into vast structures spanning millions of light years. These tiny, ephemeral ripples were magnified, giving rise to the complex cosmic web that now cradles galaxies, stars, and planets. The concept that such imperceptible quantum jitters could ultimately forge an entire universe is both exhilarating and profoundly unsettling. If our universe did indeed spring from a quantum fluctuation, it raises the startling possibility that it is merely one of countless others. Some physicists propose that the universe we inhabit is but a single manifestation in an immense multiverse, where quantum fluctuations continuously spawn new universes, each governed by its own distinct laws of physics. In this view, what we perceive as reality is only a fragment of a vast, unseen cosmic landscape, where universes emerge, evolve, and vanish in a constant, inexhaustible cycle. The discovery of quantum fluctuations has fundamentally altered our conception of emptiness. Regions of space that seem barren are, in truth, alive with hidden energy, a restless potential that may have given birth to everything we know. More astonishingly, this suggests that the universe may not require a conventional cause to exist. In our everyday world, events always follow cause and effect. But quantum mechanics operates under entirely different rules, where particles spontaneously appear and vanish, and energy can materialize or disappear without warning. Within this strange quantum arena, a single fluctuation may have sparked the birth of the entire universe, challenging every assumption we hold about creation and the very nature of reality. If the cosmos emerged from quantum fluctuations, it implies that randomness lies at the heart of existence. The idea that an entire universe could originate from an almost imperceptible ripple in the fabric of quantum energy stretches the imagination to its limits. It compels us to confront one of the most profound mysteries of all time. How did existence itself arise from what seems like nothing? Quantum mechanics, the science that probes the minutest constituents of reality, offers an unexpected answer. What we call empty space is not empty at all. Instead, it is a dynamic, invisible arena brimming with potential energy, constantly shifting in ways beyond human perception. Imagine a cosmic stage where invisible forces flicker and surge, where tiny bursts of energy ignite and vanish like ephemeral sparks. Though these fluctuations seem trivial, under the right conditions, they can catalyze events of unimaginable scale, potentially seeding entire galaxies, stars, and even the universe itself. Through the lens of quantum field theory, scientists explore this extraordinary phenomenon, seeking to understand the mechanisms that transform minute energy shifts into vast cosmic structures. The field is nascent, filled with tantalizing questions. How did the chaotic dance of quantum fluctuations give rise to the order and complexity we observe today? Which forces guided this metamorphosis from disorder into the structured cosmos we inhabit? Our understanding of creation is being fundamentally reshaped. Rather than envisioning the universe as the product of an external force or divine intervention, we are beginning to recognize it as an emergent property of space itself, birthed from its inherent, strange, and potent characteristics. As researchers delve deeper, reality reveals itself to be far more intricate, more astonishing, and far stranger than previously imagined. Creation may not have been a singular event billions of years ago, but an ongoing dynamic process, a continuous cycle of formation and dissolution, perpetually unfolding within the hidden realm of quantum physics. In this domain, the boundary between nothing and something is tenuous. Space that seems void is in fact a seething reservoir of energy, ready to produce the extraordinary when conditions align. The birth of our universe emerges not as a unique, one-time occurrence, but as part of a perpetual cosmic rhythm. Imagine an invisible dance where the potential for entire worlds exists at every instant. The quantum vacuum, once assumed to be a barren void, is in reality a roiling sea of energy, ever fluctuating, where even the tiniest perturbations can set the stage for the creation of galaxies, stars, and planets. Among the most profound ideas in cosmology is the theory of cosmic inflation, also known as cosmological inflation. In the universe's earliest moments, this theory suggests expansion occurred at an incomprehensibly rapid pace, stretching a minuscule point into a vast expanse in a heartbeat. Following this explosive growth, expansion slowed, but billions of years later, more than 7 billion years after the universe's birth, it began accelerating again, driven by a mysterious force we call dark energy, still largely enigmatic to science. The concept of cosmic inflation arose in the late 1970s and early 1980s, pioneered by brilliant minds, including Alexei Starobinsky from the Landau Institute for Theoretical Physics, Alan Guth from Cornell University, and Andrei Linde from the Lebedev Physical Institute. Their groundbreaking insights earned them recognition, such as the Kavli Prize in 2014. Inflation is crucial because it offers a plausible explanation for one of cosmology's deepest puzzles, the origin of large-scale cosmic structures. Minute quantum fluctuations during the inflationary period were stretched to immense scales, ultimately seeding galaxies, clusters, and the cosmic web itself. Inflation also sheds light on why the universe appears uniform on large scales, why the cosmic microwave background radiation is evenly distributed, why space seems flat, and why elusive magnetic monopoles remain undetected. Although the precise cause of inflation remains uncertain, theories propose the existence of a special field, the inflaton, which drove the rapid expansion faster than light for a fleeting instant before decelerating. Observational evidence increasingly supports inflation. In 1992, the COBE satellite detected minuscule temperature variations in the cosmic microwave background, as predicted, and subsequent measurements from the WMAP satellite provided even stronger confirmation. The story of the universe, from its quantum origins to the vast cosmic tapestry we observe today, is a narrative of astonishing transformation. From the flicker of microscopic energy fluctuations to the sprawling galaxies scattered across the cosmos, every structure, every particle, every star is a testament to the extraordinary power of quantum mechanics and the inexhaustible potential hidden within the fabric of space itself. However, not every scientist is convinced, and there remains a significant contingent of researchers who question whether inflation ever truly occurred. The notion that the universe is expanding traces back almost a century to the early 1930s, when astronomer Edwin Hubble made a discovery that would forever alter humanity's understanding of the cosmos. He observed that light emitted from distant galaxies was redshifted, a clear indication that these galaxies were moving away from us. Even more remarkably, the farther a galaxy was from Earth, the faster it seemed to recede. This observation shattered the long-held belief in a static universe. Instead of standing still, the cosmos was stretching, growing, and evolving. Yet Hubble's revelation was preceded by theoretical predictions from two pioneering scientists, Alexander Friedmann and George Lemaitre. Drawing on Einstein's general theory of relativity, they suggested that the universe was not only dynamic, but had been set in motion by an initial powerful push. Gravity, they argued, had never possessed the strength to halt this outward flight of matter. This concept hinted at something even more profound: cosmic inflation, a potential missing link in the intricate puzzle of the universe's origin. Friedman's equations implied that a special type of energy with negative pressure could generate an enormous repulsive force, causing space itself to expand at an exponential rate. This extraordinary energy might have originated from a quantum field trapped temporarily in a false vacuum state, a condition where energy lingers at a higher level before eventually settling into a more stable configuration. In 1979, physicist Alan Guth brought this idea into sharper focus, proposing that this inflationary expansion could also solve one of the nagging mysteries of particle physics: the absence of exotic particles such as magnetic monopoles. According to the theory, inflation would have spread these particles across such vast distances that their presence became vanishingly rare, explaining why physicists had never detected them. Beyond this, inflation provided answers to two other profound cosmic riddles. The first, known as the horizon problem, asked how regions of the universe separated by billions of light years could exhibit almost identical properties. Inflation suggested that these regions had once been tightly packed together before being flung apart at phenomenal speeds, allowing them to share the same thermal conditions. The second, the flatness problem, questioned why space appears geometrically flat rather than curved. Inflation provided a solution. The rapid expansion would have stretched any initial curvature so extensively that the universe would appear perfectly flat to observers like us. Picture looking up at the night sky, aware that your view is limited not by mountains or clouds, but by the expansion of space itself. Just as standing on Earth allows you to see a horizon where land and sky appear to meet, the universe has its own boundary, known as the cosmological horizon. This marks the maximum distance from which light has had time to reach Earth since the universe began. Beyond this horizon, space is expanding so rapidly that light from those distant regions will never arrive. The observable universe, therefore, represents only a tiny fraction of the total cosmos. There exist regions so remote that no signal or photon has ever had a chance to reach us, lying forever beyond our cosmological horizon, which scientists estimate to be roughly 46 billion light-years away in all directions. In the framework of a traditional Big Bang, without the inflationary addition, the cosmological horizon gradually expands over time, unveiling new sections of space. Yet an intriguing puzzle arises. Whenever we observe a newly revealed region, it appears almost identical to every other part of the universe. Its background radiation, the faint afterglow of the Big Bang, shows nearly uniform temperatures. Its curvature, the bending of space by gravity, aligns seamlessly with the rest of the cosmos. How could regions never in contact share such precise characteristics? Inflation offers the answer. In the universe's earliest moments, space underwent an extraordinary, almost inconceivable rate of expansion driven by a powerful energy field, often referred to as vacuum energy or a cosmological constant. Unlike ordinary expansion, this process effectively froze the cosmological horizon at a fixed distance. Regions of space were propelled apart at tremendous speed, preventing direct communication, yet all originated from the same small, uniform domain. As a result, even when stretched across incomprehensible distances, these regions retained identical temperatures and curvatures. When inflation eventually slowed and the energy field dissipated, the universe transitioned to a more moderate expansion. Those regions pushed beyond the horizon gradually re-entered our view, appearing as they always had, preserving their remarkable uniformity. Inflation also makes striking predictions about the universe's overall geometry. It implies a flat universe, where the combined density of normal matter, dark matter, and residual energy precisely equals a critical value. Observational evidence strongly supports this, with measurements of cosmic microwave background radiation confirming the predicted flatness. Moreover, inflation accounts for tiny variations in this radiation, minute fluctuations caused by quantum effects during the rapid expansion, many of which have been verified by observation, lending further credibility to the theory. In a universe experiencing accelerated expansion, objects initially close together gradually drift apart unless bound by gravitational forces. From the perspective of any one object, surrounding space behaves similarly to a black hole inverted, where crossing a boundary, a personal event horizon, prevents return. Even light from beyond this horizon can never reach the observer. This phenomenon, known as de Sitter space, requires a specific form of energy, the cosmological constant, which remains unchanged over time, sustaining the exponential expansion. In perfectly exponential inflation, the vacuum energy generates a pressure that exactly counterbalances its energy density. In reality, however, most inflationary models exhibit a slightly slower expansion, allowing the horizon to grow gradually as vacuum energy diminishes. This nuanced difference enables scientists to make precise predictions about the early universe, many of which align seamlessly with contemporary observations, painting an intricate portrait of cosmic evolution from the earliest instance to the vast universe we inhabit today. When the universe was very young, it passed through a breathtaking transformation. This was a period so brief and yet so powerful that it reshaped the very destiny of everything that exists. Scientists call it inflation, a phase of unimaginable expansion in which the cosmos ballooned at a rate beyond ordinary comprehension. In a fraction of a second, space itself stretched, smoothing out every wrinkle, erasing almost every trace of irregularity. Whatever differences in temperature or density had been present were pulled apart, leaving behind a canvas that was astonishingly uniform. In this instant, the universe lost much of its complexity, shedding its scars, becoming nearly identical in all directions. It was governed almost entirely by a mysterious entity known as the inflaton field, a hidden force that carried the energy needed to fuel this extraordinary event. But inflation did not leave the cosmos completely featureless. At the smallest possible scales, tiny quantum fluctuations remained. These were minute variations, ripples in the energy field itself, nearly invisible yet vital. Over billions of years, gravity would take these ripples and amplify them, turning them into the seeds of galaxies, stars, and planets. Without them, the night sky would be empty, a dark expanse without structure. Inflation had cleared the stage, but it also left behind the faintest marks of possibility, faint blueprints for everything that would follow. This rapid expansion also erased exotic relics predicted by certain theories of particle physics. Some scientists had speculated about magnetic monopoles, hypothetical heavy particles that should have been created in great numbers if the universe had once been hot enough. Yet inflation stretched the fabric of space so violently that these particles, if they had existed, became impossibly rare. To find one today would be like searching a desert for a single grain of gold. The process is described by a principle borrowed from black hole physics, known as the no-hair theorem of inflation. Just as black holes shed all defining details except mass, charge, and spin, the universe in the aftermath of inflation shed nearly every imprint of its early chaos, leaving behind simplicity, uniformity, and near emptiness. The scale of this transformation is staggering. As the universe expanded, the density of matter and energy plummeted. Dust and ordinary matter thinned as space doubled in size, their density falling by a factor of 8. Radiation, which not only spread but also lost energy to stretched wavelengths, thinned even faster, its density falling by a factor of 16 with every doubling. Yet the inflaton field itself remained strangely steady, its energy undiminished, dominating everything else. Ordinary particles, curvature, irregularities, even exotic relics were reduced to near insignificance. By the end of this cosmic storm, the universe was extraordinarily flat, overwhelmingly uniform, and, in a sense, empty. Inflation was also a time of chilling transformation. The temperature of the cosmos plummeted, dropping by a factor of 100,000. Early models suggest a fall from around 10 to the power of 27 Kelvin to about 10 to the power of 22 Kelvin, a staggering collapse in heat. Yet this descent was not permanent. When inflation came to an end, the enormous stored energy of the inflaton field was released in a burst of creation. Space reheated in an instant, a process known as thermalization, filling itself with a sea of particles, radiation, and the ingredients of matter. This was the true dawn of the hot Big Bang, the beginning of the universe's radiation-dominated age. Stars, galaxies, and the complex structures we see today were still unimaginable, but the furnace of possibility had been lit. And yet, even with its explanatory power, inflation remains mysterious. The true nature of the inflaton field is unknown. Was it a kind of false vacuum, an unstable energy state waiting to collapse? Was reheating triggered by a process called parametric resonance, in which energy cascaded out of the field with violent efficiency? These are questions that physicists still grapple with, even as the theory of inflation has solved many of the puzzles that haunted cosmology in the 20th century. In the 1970s, the Big Bang theory faced troubling questions. Why was the universe so uniform? Why was it so flat? Why had we not detected magnetic monopoles? In 1979, a young physicist named Alan Guth offered an idea that would transform cosmology. If the universe had once been trapped in a false vacuum, a peculiar energy state, it could have triggered runaway expansion. Space would have stretched exponentially, erasing monopoles, ironing out irregularities, and setting the stage for the cosmos we inhabit. What began as an attempt to explain the absence of a hypothetical particle soon became a sweeping theory of the origin of order itself. One of the deepest mysteries was the horizon problem. The cosmic microwave background, a faint glow of radiation from the early universe, is almost perfectly uniform in temperature. But according to the standard Big Bang model without inflation, this should not be possible. Regions of the sky now billions of light years apart could never have been in contact. They were always too far apart, moving away from each other faster than the speed of light, unable to share heat or information. Yet somehow, their temperatures matched with extraordinary precision. To understand this paradox, imagine a sealed canister of gas. Over time, the gas molecules collide, spreading out evenly until the temperature becomes uniform. But the early universe without inflation had no time for such balancing. How then did the cosmos become so even? Earlier attempts to solve this problem faltered. Georges Lemaitre and Richard Tolman suggested a cycling universe of expansion and contraction, but entropy buildup made the idea untenable. Charles Misner proposed a chaotic early phase, the Mixmaster model, in which turbulence might smooth things out. Later analysis showed this would not work either. Inflation, however, offered a simple answer. If the universe had once been far smaller, then all regions we see today were once close enough to interact, to exchange heat, to reach balance. Then, with inflation, they were torn apart, carried to unimaginable distances. This is why the cosmic microwave background appears uniform. It was balanced when the universe was small, and inflation preserved that balance by stretching it across the sky. Another enigma is the flatness problem. Observations reveal that space follows the rules of Euclidean geometry with extraordinary precision. Parallel lines stay parallel. Triangles add up to 180 degrees. This flatness requires the density of the universe to be tuned almost exactly to a critical value. Any deviation would have grown over billions of years into a visible curvature, bending space into a sphere or a saddle. The fact that we live in a universe so flat is an improbable coincidence without inflation. But with inflation, the mystery dissolves. The expansion dilutes curvature, driving the universe toward flatness, much as the surface of an inflating balloon appears flatter and flatter from close up. Inflation explains not only the shape of space, but why its shape is so precisely balanced. From its beginnings, inflation was not simply a solution to equations. It was a revolution in our understanding of creation itself. It showed that the smoothness, the flatness, the structure, and even the very possibility of galaxies and stars all stem from a brief, furious, silent expansion. Out of this fleeting moment of violence came the foundation of order, and out of that order came the cosmos we see around us. The story of inflation is the story of how everything began, how chaos became simplicity, and how simplicity gave rise to the complexity of a universe filled with stars, planets, and life. However, in a universe without inflation, if we rewind the cosmic clock back through the ages, the delicate balance of conditions becomes ever more precarious. At the epoch of Big Bang nucleosynthesis, when the very first nuclei and atoms began to form, the geometry of space itself had to be tuned with an almost impossible precision. The curvature of the universe needed to be 1 part in 10 quadrillion, a 1 followed by 16 zeros. If the balance had been off by even the slightest fraction, the cosmos would have either rushed outward so quickly that galaxies, stars, and planets could never have emerged, or it would have collapsed back upon itself before structure could take root. Inflation provides a remarkable resolution to this paradox. By stretching space in an unimaginably short burst of rapid expansion, any initial curvature is smoothed away. The analogy is simple. As you inflate a balloon, its surface becomes flatter from the perspective of an observer standing on it. The result is the vast, nearly flat universe we measure today. Grand unified theories, or GUTS, add another layer to this story. According to these ideas, the fundamental forces we know, electromagnetism, the strong nuclear force, and the weak nuclear force, were once not separate but part of a single, unified force during the first instance of cosmic history. As the universe cooled, this unified state fractured, much like water crystallizing into ice. But with this elegant prediction came an apparent problem. GUTS suggested that magnetic monopoles, hypothetical particles carrying only a north or south magnetic charge, should have been produced in great abundance. If that were true, our universe should be teeming with them today. Yet no experiment, no observation has ever uncovered even a single monopole. Inflation sweeps this problem away with surprising ease. If the universe expanded explosively in its earliest moments, these particles would have been spread across such inconceivable distances that any surviving today would be impossibly rare, far beyond our reach. In essence, inflation diluted them into practical invisibility. And yet, as Martin Rees once quipped, one could humorously argue that it is a convenient triumph to declare you have solved a problem when the very thing you set out to solve may never have existed at all. Even so, inflation remains our most convincing explanation for their absence. The seeds of this theory stretch back to the early 20th century. When Albert Einstein unveiled general relativity, he introduced into its equations a peculiar mathematical device, the cosmological constant. He added it not out of whim, but from a conviction shared by many scientists of the era, that the universe must be static, neither expanding nor contracting. His model pictured space as a great three-dimensional sphere filled uniformly with matter. Yet the Dutch physicist Willem de Sitter found another solution buried in the equations, one that contained no matter at all, but was driven to expand rapidly by the cosmological constant alone. Einstein's model, it turned out, was inherently unstable, teetering on the edge. A slight nudge could send it collapsing inward or ballooning outward into something akin to de Sitter's runaway expansion. By the mid-1960s, new voices were adding strange and daring ideas to the conversation. A physicist named Peter Higgs had already shaken the community with the idea that fields could endow particles with mass, and around the same time, another researcher, often overlooked, proposed that pressure in the infant universe may not have behaved as expected. Instead of exerting an outward push, it could have been negative, pulling space in peculiar ways directly tied to energy density. Though largely ignored at first, this concept would later resurface as the earliest hint of dark energy, the mysterious entity now believed to dominate the cosmos. In the early 1970s, cracks began to appear in the Big Bang model. Yakov Zeldovich, one of the leading Soviet physicists, identified two glaring puzzles. The first was the flatness problem. Why is the universe so extraordinarily close to flat rather than curved, as one might naturally expect? The second was the horizon problem. How could distant regions of the cosmos, separated by more distance than light could have traveled since the beginning, display nearly identical temperatures and properties? Up to that point, many had shrugged and attributed such smoothness to coincidence. But coincidence was a weak foundation for science. In Moscow, Zeldovich and colleagues like Vladimir Belinsky and Isaac Kolotnikov turned their attention to the mathematics of chaos, developing what became known as the BKL singularity, a scenario where the early universe might have been wildly chaotic before settling into the order we observe. Across the ocean, Charles Misner in the United States crafted his Mixmaster universe, another attempt to tame these mysteries through the mathematics of disorder. Both efforts illuminated possibilities, but neither offered a complete resolution. As the decade wore on, physicists turned to quantum mechanics for answers. Sidney Coleman applied techniques first pioneered by Alexander Polyakov and others, exploring how unstable quantum states could suddenly leap into more stable ones. The universe, he imagined, might behave like supercooled water waiting for a seed of ice to trigger freezing. A tiny bubble of true vacuum could have been the spark that ignited expansion. But Coleman had not yet considered how gravity itself would sculpt this transformation, nor how it might drive the grand unfolding of the cosmos. By the late 1970s, the boldest ideas emerged. Some physicists dared to suggest that the universe itself could have arisen from nothing. No space, no time, no matter. The engine for this creation would be quantum fluctuations, those restless energy tremors that pop particles in and out of existence. Robert Brute, Francois Englert, and Edgard Gunzig advanced a radical proposal. Perhaps our universe began as a random fluctuation in empty space, which then entered a de Sitter-like expansion before transitioning into the familiar Big Bang expansion we observe today. This picture reframed the very concept of a beginning, replacing it with a transition. Meanwhile, in the Soviet Union, Alexei Starobinsky presented a breakthrough of his own. He showed that in spacetime's curve to an extreme, quantum effects would generate an inflationary expansion naturally, almost inevitably. His model not only solved the flatness and horizon problems highlighted by Zeldovich, but also predicted faint imprints in the cosmic microwave background, the afterglow of the Big Bang. Decades later, satellites would measure those very imprints. Around this same period, Zeldovich identified another vexing conundrum, the monopole problem, now framed not just as a cosmological curiosity, but as a concrete challenge for particle physics. If magnetic monopoles were inevitable, why were they not observed? In 1980, a young American physicist named Alan Guth found the key. He realized that if the universe became trapped in a high-energy state, a false vacuum, then, as it cooled, it could erupt into a phase of exponential expansion. Inflation was born. Guth likened it to supercooled water. It can remain liquid below freezing until a disturbance crystallizes it into ice. In this cosmic analogy, the disturbance released the universe from its false vacuum, and space itself exploded in size. Almost simultaneously, Demosthenes Kazanas argued that inflation also resolved the horizon problem, while Katsuhiko Sato pointed out that inflation could erase unwanted relics like domain walls, hypothetical structures that would have otherwise filled the cosmos. In 1981, David Einhorn and Eric Steinhardt expanded on these ideas, showing that inflation not only explained the absence of monopoles, but also addressed other puzzles haunting cosmology. Yet challenges remained. The simplest models of inflation required exquisite fine-tuning of constants, and rapid expansion risked creating density variations too extreme to match what we observe today. Guth refined his model further, envisioning a universe trapped in a false vacuum, whose bubbles of true vacuum expanded at the speed of light, consuming the false vacuum and reshaping the cosmos forever. However, Guth soon recognized that his pioneering proposal carried a serious weakness. His version of inflation could not explain how the universe became suffused with the heat and radiation we observe today. The mechanism he envisioned, the formation of bubbles in a false vacuum, simply was not capable of reheating the cosmos. For inflation to succeed as a full picture, something had to generate radiation. Yet in Guth's original framework, this only happened if bubbles collided. The problem was unavoidable. If inflation persisted long enough to solve the flatness and horizon puzzles, the bubbles would be separated by such enormous distances that collisions would almost never occur. This obstacle became known as the bubble collision problem, one of the earliest major challenges facing inflationary cosmology. It was not until the work of André Linde and independently Andreas Albrecht and Paul Steinhardt that a breakthrough arrived. They introduced what became known as the new inflation, or slow roll inflation, a model that moved beyond Guth's original formulation, now referred to as old inflation. Guth's idea had involved a sudden quantum tunneling event from a false vacuum, creating bubbles that expanded and collided in an inconsistent way. By contrast, new inflation proposed that the expansion of space was driven by a scalar field that drifted gently down an energy slope, more like a ball rolling slowly down a broad hillside than a violent tunneling event. As long as the slope remained shallow, inflation would proceed at an exponential pace, stretching the universe to unimaginable scales. Eventually, when the slope steepened, inflation ended, triggering a phase of reheating in which the energy stored in the field transformed into matter and radiation. This process set the stage for the hot Big Bang and for the birth of the universe as we know it. But the elegance of new inflation came with an unexpected twist. Instead of leaving the cosmos perfectly smooth, it introduced tiny quantum fluctuations in the inflaton field itself. These minute irregularities, magnified by inflation's exponential expansion, became the primordial seeds from which galaxies, stars, and clusters of matter would later grow. The first theoretical calculations of these fluctuations were carried out by Vyacheslav Mukhanov and Gennady Chibisov, inspired by a related model proposed by Alexei Starobinsky. In the early 1980s, further breakthroughs emerged during the Nuffield Workshop on the Very Early Universe, held at Cambridge University in 1982. For 3 weeks, many of the leading physicists of the era gathered and independently arrived at the same conclusion. Inflation inevitably generated quantum fluctuations. Stephen Hawking, Alexei Starobinsky, Alan Guth with So-Young P., and the team of James Bardeen, Paul Steinhardt, and Michael Turner each confirmed that these fluctuations were not only real, but central to cosmic structure formation. Despite its rocky beginnings, inflationary theory matured into one of the central pillars of modern cosmology. Its explanatory power was immense. It showed why the universe appears nearly uniform in every direction, why space looks astonishingly flat, and why hypothetical relics like magnetic monopoles predicted by particle physics are so rare as to be effectively absent. Since Guth's first proposal in the late 20th century, mounting evidence has consistently strengthened the case for inflation. Among the most powerful confirmations came from the Planck spacecraft's meticulous observations of the cosmic microwave background. These measurements revealed a universe that is flat to within 1/2 of 1%, a margin so precise it leaves little room for alternatives. They also demonstrated that the cosmic structure is almost perfectly uniform, with tiny variations only once in every 100,000 regions. According to inflationary theory, these faint variations are exactly what gave rise to all the cosmic architecture we see today. The fluctuations were quantum in origin, ripples of energy in the inflaton field that gravity later amplified into galaxies and superclusters. Scientists describe this pattern as a nearly scale-invariant Gaussian random field, a precise statistical fingerprint that inflation predicts. The pattern is controlled by just 2 fundamental numbers, one that fixes the overall strength of the fluctuations, and another that slightly tilts the spectrum away from perfect uniformity. Another prediction involves the tensor to scalar ratio, which measures the relative strength of primordial gravitational waves to scalar energy fluctuations. Simple models suggest this ratio should be about 1/10. Crucially, inflation also predicted that the universe's earliest fluctuations would be in thermal equilibrium, balanced in a way that later measurements could test. Observations from WMAP, Planck, and vast galaxy surveys like the Sloan Digital Sky Survey confirm this prediction with remarkable accuracy. The spectral index, which measures deviations from perfect scale invariance, is predicted by the simplest models to fall between 0.92 and 0.98. Planck's data revealed a value of roughly 0.97, aligning beautifully with expectations. Over time, many different versions of inflation have been proposed, each with its own refinements and peculiarities, though most require careful fine-tuning of parameters to match the data. Even so, inflation's strength lies in its economy. With only 2 key numbers, it predicts the universe's initial conditions with impressive fidelity. Occasionally, new results appear to cast doubt on inflation, but these often fade with better data. Early WMAP findings hinted at possible irregularities, but later studies showed they were likely statistical flukes. More puzzling was the discovery that some microwave background fluctuations seemed aligned with the plane of the solar system. Whether this is a genuine clue to new physics, a quantum effect, or an observational bias remains unsettled. Scientists continue to probe inflation's predictions with ever greater precision. One major goal has been the search for B-modes, subtle patterns in the polarization of the cosmic microwave background that would signal gravitational waves from inflation itself. In 2014, the BICEP 2 telescope team announced a dramatic of B-modes, estimating a tensor to scalar ratio between 0.15 and 0.27. The result generated enormous excitement, but by mid-2014, confidence had waned, as evidence mounted that interstellar dust could explain the signal. By 2018, new data showed that the ratio was no higher than 0.06, and the initial claims of detection faded into history. The search continues, however, with new instruments on Earth and in space, and fresh strategies like mapping 21-centimeter radiation from primordial hydrogen. If successful, this approach could offer an even clearer window into the infant cosmos, though formidable challenges such as interference from human-made radio signals still stand in the way. When Guth first introduced inflation, some wondered whether the Higgs field, the field that gives mass to elementary particles, might itself be the inflaton. For a time, the idea was attractive, but it eventually clashed with experimental data at the electroweak scale. As a result, attention shifted toward other possibilities, including grand unified theories that attempt to merge the fundamental forces of nature. These searches continue as physicists seek the elusive mechanism that ignited inflation and set the universe on its present course. From its troubled beginnings to its present role as a cornerstone of cosmology, inflation has transformed our understanding of the universe's earliest moments. It turned a puzzling patchwork of observations into a coherent narrative, linking quantum mechanics, gravity, and the vast sweep of cosmic history. And while many mysteries remain, the idea that the universe underwent a brief, extraordinary burst of exponential expansion endures as one of the most profound insights of modern science. And one of the greatest obstacles in inflationary theory lies in what scientists call fine-tuning. To put it simply, inflation can only take place if the universe begins under conditions that are almost impossibly precise. In the framework of the so-called new inflation model, these requirements become very restrictive. The field that drives inflation, called the inflaton, must obey what are known as slow roll conditions. These conditions demand that the inflaton's potential energy landscape be smooth and gentle compared to the overwhelming vacuum energy of the early universe. The inflaton itself must also be extraordinarily light, possessing a mass so small that it seems unnatural when compared to other known particles. The theory therefore insists on a very special type of scalar field with an almost perfectly flat potential and with initial conditions arranged with remarkable care. This strange demand for delicately chosen parameters has inspired physicists to search for mechanisms that might make such precision inevitable. One intriguing possibility comes from scale-invariant field theories, mathematical frameworks in which the equations describing a system remain unchanged, no matter the scale at which they are applied. If scale invariance is slightly broken by subtle quantum effects, the inflaton's potential could naturally flatten out. The result would be a field that automatically satisfies the slow roll requirements without deliberate fine-tuning. But this explanation depends critically on the tools of perturbation theory, a method that only works if the underlying physics remains tame enough to allow small corrections to dominate over large ones. In the 1980s, André Linde offered a bold alternative. His idea, called chaotic inflation, challenged the belief that only finely prepared conditions could spark inflation. Instead, he proposed that inflation could ignite almost anywhere if the universe began in a high-energy, disordered state. In this vision, the inflaton's potential is unbounded, stretching beyond 1 Planck unit, the smallest meaningful scale in physics. Such scenarios are known as large field models, while the more delicate new inflation frameworks are referred to as small field models. Chaotic inflation avoids the extreme precision problem, but it comes at a cost. According to effective field theory, if the inflaton takes values larger than the Planck scale, the rules of the theory may break down. The mathematical procedure of renormalization, designed to cancel infinities and keep predictions meaningful, could instead produce corrections so large that the inflationary mechanism is destabilized. This tension between naturalness and mathematical consistency remains unresolved. The difficulty does not end there. Even if inflation occurs, the energy scale at which it does so presents another puzzle. Observations of the tiny fluctuations that seeded galaxies and galaxy clusters point to an inflationary energy of about 10 quadrillion giga-electron volts, roughly 1,000th of the Planck energy. The Planck scale is the most natural energy benchmark in physics, so the fact that inflation operates far below it appears to introduce yet another kind of fine-tuning, one known as the hierarchy problem. And yet many theorists argue that this is not a fatal flaw. The inflationary scale aligns closely with the energy range where the fundamental forces of nature might unify, hinting that this apparent coincidence may instead be a clue to a deeper connection. As the theory evolved, it became clear that inflation might not simply end everywhere at once. Many models predict that while inflation halts in certain regions, it persists elsewhere, continuing to expand those patches at extraordinary speed. If the transition out of inflation proceeds too slowly, new inflating regions form faster than old ones vanish. The result is eternal inflation, a cosmic process in which the universe as a whole never ceases inflating. On vast scales, inflation dominates the cosmic volume, perpetually spawning new regions in which inflation still rages. This picture leads to a dramatic implication: an ever-growing multiverse, an infinite collection of universes branching endlessly from one another. The notion of a multiverse has ignited fierce debate. To some, it is the natural and unavoidable outcome of inflationary physics. To others, it undermines the very foundation of science by producing predictions that cannot be tested. In the early 1980s, Paul Steinhardt, one of the original architects of inflation, became the first to suggest that inflation could be eternal. He described a universe filled with hot, dense bubbles of ordinary space forming within the inflating background. Yet these bubbles expand too slowly to overtake the surrounding inflationary sea. Instead, inflation continues outside, ensuring the process never ends. Later, Alexander Vilenkin demonstrated that eternal inflation emerges generically across many inflationary models. The inflaton field, instead of steadily rolling down its potential like a ball on a hill, can be nudged upward by random quantum fluctuations. When this happens, new inflating patches arise, and because regions of higher energy expand more rapidly than those of lower energy, they dominate the universe's growth. If the inflaton has no upper bound, this process is endless. But eternal inflation introduces profound mathematical challenges. Inflationary space resembles de Sitter space, a simple model of accelerated expansion. However, de Sitter space cannot extend infinitely into the past. It must have a beginning. Likewise, an eternally inflating cosmos cannot be past eternal. Sooner or later, the chain of inflationary expansion must trace back to an initial singularity, a point where density and energy become infinite. In this sense, inflation postpones but does not eliminate the problem of cosmic origins. Scientists still seek a theory of quantum gravity capable of describing the first moment when time and space themselves may have emerged. Meanwhile, the dynamics of eternal inflation lead to a striking asymmetry. Inflating regions expand exponentially, while regions where inflation has ended do not. No matter how many non-inflating bubbles form, the volume of the universe dominated by inflation always dwarfs them. On cosmic scales, inflation never relinquishes its grip. The story of the universe, as told by inflationary theory, is not one of a singular beginning followed by a straightforward evolution, but of a sprawling, self-reproducing multiverse, forever seeding new realms, each with its own physical laws, structures, and possibilities. However, inflation eventually comes to a halt in certain regions, and when it does, it sets the stage for the birth of structure. Galaxies take shape, stars ignite, planets emerge, and the cosmic tapestry begins to unfold. But behind this seemingly ordered picture lies one of the most heated debates in modern physics: how to make sense of probabilities across an imagined multiverse that is, in many theories, endlessly inflating. Some researchers insist that inflation is eternal, that in the vast majority of the cosmos, it never ends, forever creating new patches of space. Others counter that the very fact we exist to observe the universe implies that inflation must have stopped somewhere, otherwise conscious beings could never arise. The paradox grows sharper when physicists try to calculate what came before inflation, if such a thing can even be defined. Some propose that the problem could be resolved by examining the amount of space that might have existed before inflation ever began. Others regard this as evidence of a deeper flaw in the theory itself, a fundamental inconsistency at the heart of inflationary cosmology. Among the most striking reversals in science came from Paul Steinhardt, one of the original architects of eternal inflation, who later became one of its fiercest critics, arguing that the very framework he helped build could be fatally problematic. In an effort to sidestep these difficulties, some scientists have proposed a more radical picture. The universe had no beginning at all. In this view, it has always existed, without a moment of creation. It stretches infinitely, expanding without end at an ever-increasing rate. Yet other theories argue that the universe did indeed emerge from nothing, born out of quantum fluctuations and the strange mechanisms of cosmic inflation. Among these, physicist Alexander Vilenkin put forward the idea that the cosmos could spontaneously arise from nothingness, while Stephen Hawking and James Hartle developed what became known as the no-boundary proposal. Their model suggested that the universe did not require a sharply defined starting point. Instead, it flowed smoothly into existence, passing through inflation naturally as part of its earliest history. Alan Guth, the pioneer of inflation theory, once described the process as the ultimate free lunch. He proposed that entire new universes, each potentially resembling our own, could bud off within a vast, expanding cosmic background. In this framework, gravity assumes an unusual role. While physics generally demands that energy must be conserved and that disorder or entropy must always increase, gravity seems to bend these rules without violating them. Under certain conditions, it allows for the spontaneous generation of whole universes while still remaining consistent with fundamental laws. Yet the theory has not gone unchallenged. Don Page, a physicist and collaborator of Hawking, voiced skepticism that inflation actually solved the puzzle of the universe's initial conditions. Instead, he argued, inflation required the universe to have started in a far more ordered, low-entropy state than even traditional Big Bang models suggested, making the problem of fine-tuning even worse. If inflation raised entropy, then the original conditions would have had to be impossibly neat and precise. For Page, this deepened rather than answered the mystery of how the cosmos began. When he and Hawking attempted to compute the probability of inflation, their calculations produced results too ambiguous to settle the question. Some researchers argue that the ambiguity does not matter, because once inflation begins, its nature is to continue indefinitely, creating pocket universes without end. As long as the chance of inflation occurring is not zero, it inevitably dominates. Physicists Andreas Albrecht and Lorenzo Sorbo went further, suggesting that inflationary universes are overwhelmingly more likely than alternatives. Their reasoning was that inflation requires less initial energy to ignite than non-inflationary scenarios, tipping the balance heavily in its favor. But new complications arise when considering the trans-Planckian problem. Inflation took place at energy scales uncomfortably close to the Planck scale, the smallest meaningful unit in physics. This means that quantum fluctuations in the early universe could have existed at scales even smaller than the Planck length. If so, then unknown laws of quantum gravity may have left imprints on the cosmos. Some argue that these effects would be negligible, invisible to observation, while others maintain that they could have profound consequences for understanding how space itself came into being. To address these puzzles, variations of inflation have been introduced. Hybrid inflation, for instance, built on earlier models and introduced the idea of multiple interacting energy fields. In this picture, one field drives the rapid expansion while another field acts as a trigger to bring inflation to a sudden end. This neatly avoids the endless continuation of eternal inflation and allows the universe to move into new evolutionary stages. Hybrid inflation carries a resemblance to the mysterious force we now call dark energy, which today drives the accelerating expansion of the cosmos. Yet the energy scale is vastly different. Dark energy operates at around 10 to the power of minus 12 giga-electron volts, a value about 27 orders of magnitude lower than the colossal energies of inflation. A remarkable breakthrough arrived with the development of flux compactifications, linking the inflationary framework to the mathematics of string theory. One striking variation, known as brane inflation, imagines that inflation is triggered by the motion of higher dimensional objects called d-branes within the hidden geometry of extra dimensions. As these branes move and interact with their counterparts, the energy released can drive inflation in a manner distinct from classical models. This vision places the origin of cosmic expansion within a much broader theoretical landscape, suggesting that our universe's birth may be tied to the hidden fabric of dimensions beyond the three of space and one of time that we can perceive. However, scientists still do not fully grasp the hidden mechanisms behind these extraordinary processes. Inflation, in one scenario, appears to unfold through a strange phenomenon reminiscent of the older inflationary models, where the young universe undergoes a quantum leap, tunneling from one state of reality into another. This transition, sudden and dramatic, would not be enough on its own. Afterward, a separate mechanism must have taken over, stretching the fabric of space with unimaginable force and speed, completing the phase of inflation that shaped the cosmos. Another striking approach emerges from the ideas of loop quantum gravity, a theory that challenges the way we think about space itself. According to this framework, space is not infinitely smooth, but instead woven from minuscule discrete building blocks, like threads of a cosmic fabric too fine for human eyes to see. If the universe ever held too much energy for these quantum-sized units to contain, then instead of collapsing into oblivion, the universe might rebound. This bounce could provide a startling alternative explanation for the origin of inflation, replacing a catastrophic end with an eternal renewal. At the heart of these competing ideas lies the same fundamental question: how did everything begin? What forces governed the earliest moments of existence and set the stage for the grand story of cosmic evolution? Scientists across generations have offered visions of these origins, each one daring to challenge accepted wisdom and reveal what might lie behind the curtain of creation. One such vision is the Big Bounce hypothesis. Rather than a singularity, a point of infinite density where the laws of physics break down, this idea proposes a cosmic rhythm: contraction followed by expansion, collapse followed by rebirth. The Big Bang in this picture was not the ultimate beginning, but instead the turning point of a greater cycle. This bounce elegantly addresses two of the deepest mysteries in cosmology: the flatness problem, which asks why the universe appears so uniform and smooth on vast scales, finds its answer in the rebound. And the horizon problem, which puzzles over how distant regions of the universe that could never have touched share the same properties, is naturally explained in this cyclical framework. Such explanations grow out of a bold extension of Einstein's general relativity. This alternative, known as the Einstein-Cartan-Siama-Kibble theory, introduces torsion, an additional twist in the geometry of spacetime that only becomes relevant under extreme conditions. When the universe was unimaginably dense, torsion acted like a hidden repulsive force, preventing matter from collapsing into a singularity. Instead of an infinite point, there existed a minimum size, a boundary beyond which collapse was impossible. Out of this smallest possible state, the universe rebounded into expansion, avoiding the paradoxes of singularities and launching the cosmos on its long journey. As the density lessened and torsion faded, the universe entered the radiation-dominated era we can trace in cosmic history. Other models push this vision even further. The ekpyrotic and cyclic theories imagine a universe without beginning or end, endlessly moving through cycles of birth and destruction. In these models, the Big Bang was merely the most recent chapter in an eternal story. The universe expands for trillions of years, then contracts into a great crunch, only to ignite once more in a blazing rebirth. These cycles echo an idea first glimpsed in the early 20th century by Richard Chase Tolman, who envisioned an oscillating cosmos. Modern versions, however, break from his finite vision. They allow for infinity itself, a universe eternal in both directions of time. Still, enormous challenges remain. Can such models account for the subtle ripples in density, the tiny variations that seeded the formation of galaxies and stars? Can the universe truly pass smoothly from crunch to bang without violating known physics? If temperatures in the crunch rise above the grand unified scale, they could create exotic particles like magnetic monopoles, yet no such relics have ever been observed. And yet, if the cycles are real, the universe's current expansion would not be slowing in any way that we could yet detect. Each cycle stretches over 1 trillion years, far beyond the reach of human observation. A different line of thought arises from string theory, a vast framework that attempts to unite all the forces of nature. In this vision, reality is not built of point-like particles, but of tiny vibrating strings. These strings weave through not only the 3 dimensions of space we know, but through hidden dimensions curled up so small they escape our senses. Among the many variations of string theory lies string gas cosmology, an idea developed by Robert Brandenberger and Qumran Vafa. They imagine the newborn universe as a seething hot gas of strings. Some strings wrapped themselves around extra dimensions, preventing them from expanding. Only 3 spatial dimensions were freed, canceling the effects of the strings, allowing them to grow large and become the vast space we inhabit today. Though elegant, the original form of this theory did not resolve every puzzle. Refinements added later, including the possibility of a cosmic bounce, helped address problems left unresolved. Yet questions remain. Can such models account for the small variations that blossomed into stars and galaxies, or are they another step on the long path toward a deeper theory, still hidden in the future? There are even theories daring enough to challenge one of the most sacred constants in physics, the speed of light. According to the variable speed of light hypothesis, in the earliest moments of the universe, light itself may have traveled far faster than today. If so, distant regions of space could have communicated and shared energy in ways otherwise impossible, erasing the horizon problem without invoking inflation. Over time, as the universe cooled and evolved, the speed of light slowed, arriving at the constant value measured by modern science. If true, this would rewrite one of the fundamental laws of reality itself. Through each of these ideas, scientists seek not just equations and predictions, but glimpses into the very foundations of existence. They are drawn by the same ancient mystery that has haunted humanity since the first person looked up at the night sky. How did it all begin? These theories, though often speculative and untested, represent bold attempts to peel back the darkness and understand the cosmic code. But alongside the question of origins lies another mystery just as profound. Are we alone in this immense, unending universe? Across centuries, poets, philosophers, and dreamers have asked whether life flourishes only here on Earth, or whether scattered among the countless stars, other worlds harbor their own forms of life. This question does not only challenge science, it challenges our sense of place in the cosmos. Today, armed with telescopes capable of gazing across unimaginable distances and instruments sensitive enough to detect the faintest signals, humanity has entered a new era in the search for extraterrestrial life. This search reaches far beyond our solar system to exoplanets orbiting distant suns. It also turns inward, re-examining the hidden corners of our own planetary system, scanning for traces of life where once we saw only barren wastelands. At the core of this quest lies a deceptively simple question. What makes a world habitable? Earth terms of life, from invisible microbes to colossal whales, from the moss clinging to stone to the redwoods towering toward the sky. What hidden balance makes this possible? What subtle alignment of conditions turned this rocky planet into a cradle of life, while others remain silent and still? One answer emerges in the form of liquid water. Every organism on Earth relies on water to survive. Water dissolves substances, enabling vital chemical reactions. It carries nutrients, stabilizes environments, and shapes the very structures of cells. Without it, life as we know it could not endure. But water does not flow everywhere. Earth has it because of its privileged place within the habitable zone, a fragile band of space around the sun where temperatures remain just right. Too close and oceans boil away like on Venus. Too far and water locks itself in ice as on Mars. Earth exists in the rarest of places where rivers, seas, and rainfall nourish an entire planet. As scientists extend their search outward, they carry this knowledge with them, scanning the stars for planets where similar conditions might exist. Somewhere, perhaps orbiting a star we cannot yet see, there could be another world balanced on the same delicate knife edge. A world where water flows, where chemistry dances, and where life in some form has taken hold. And if such a place exists, then the story of the universe may not be the story of matter and energy alone, but also the story of life, multiplied across the infinite expanse of space. However, water alone is not enough. Life demands not only liquid seas and protective skies, but also a steady supply of energy. On Earth, the great furnace in the sky, the sun, powers almost everything that breathes, grows, or crawls. Green plants trap sunlight in a delicate alchemy called photosynthesis, weaving light into food. Animals, from the smallest insects to the largest predators, feed on that energy chain, passing the sun's fire from leaf to flesh, from hunter to hunted. Entire ecosystems dance to the rhythm of the solar heartbeat. But the story does not end with sunlight. The universe has a way of surprising us. In the darkest depths of Earth's oceans, far beneath the reach of even a single stray ray of sunlight, life flourishes where no one thought it could. There, on the black seafloor, cracks in the planet's crust give birth to hydrothermal vents, spouts of heat and chemicals rushing from the fiery underworld below. Around these vents thrive alien-looking creatures, utterly detached from the sun's gift. Instead of photosynthesis, they depend on chemosynthesis, a strange metabolism that uses heat and minerals to forge life's energy. Giant tube worms, ghostly white crabs, and bacteria-coated mussels live in eternal night, feeding on the Earth's inner fire. These discoveries shattered the assumption that the sun is the only giver of life. They showed us that life can adapt to conditions utterly hostile to human senses, rewriting our definition of habitability. This revelation opens the door to a grander question. If life can prosper in the crushing pressure and scalding darkness of Earth's ocean vents, why not elsewhere? Scientists turn their eyes toward the icy moons of the outer solar system. Europa, Jupiter's enigmatic moon, hides a global ocean beneath a shell of ice thicker than any polar cap on Earth. Enceladus, a small moon orbiting Saturn, sprays jets of water vapor into space, evidence of a liquid ocean beneath its frozen crust. If heat from their rocky cores fuels chemical reactions similar to our own hydrothermal vents, then perhaps alien life thrives there too, unseen beneath layers of ice, surviving without a hint of sunlight. The possibility stretches imagination and reshapes our sense of the cosmos. Life, it seems, does not cling only to the warmth of starlight, but may rise wherever energy and chemistry dance together long enough. Yet, life requires more than water and energy. It needs stability, a steady hand of time. For life to grow, adapt, and evolve into complex forms, its home must remain hospitable not for centuries but for millions, even billions of years. Earth has been such a cradle, holding its climate, oceans, and protective shields long enough for single-celled organisms to blossom into forests, animals, and eventually human beings. Think of a seed planted in a garden. If storms tear the soil apart day after day, the seed never grows into a tree. Only when the soil, water, and sunlight remain steady does the tree rise tall. So too with planets. Stability is the hidden requirement for life to flourish. Earth's protective atmosphere is a vital part of that stability. Invisible, fragile, yet powerful, this thin veil shields us from deadly radiation pouring in from the cosmos. It balances heat, holding warmth in the cold of night and softening the blaze of day. It blocks the solar wind, a constant storm of charged particles that could strip a planet bare. Without it, Earth would be little more than a frozen wasteland bombarded by cosmic death rays, barren and silent. For other worlds to host life, they too must wear such a shield. They would need atmospheres thick enough to protect, magnetic fields strong enough to deflect, and climates steady enough to allow life's slow unfolding. Without these, a world might harbor oceans, but no creatures would ever rise to swim in them. This leads to a haunting question. How many planets share these rare gifts? To search for an answer, astronomers use a tool called the Drake equation. First proposed in 1961 by Frank Drake, it is not a solution but a framework, a way of breaking down the problem of cosmic life into smaller parts. It asks, how many stars in our galaxy host planets? How many of those planets might lie in the habitable zone, where temperatures could allow liquid water? Of those, how many actually give rise to life? How many evolve intelligence? And finally, how many civilizations reach a stage advanced enough to send signals into the void? Each factor narrows the possibilities, yet the vastness of the galaxy leaves the mind spinning. Even if only a fraction of planets meet the criteria, the sheer number of stars suggests that intelligent life should not be unique to Earth. But if that is true, why the silence? This question is the heart of what is known as the Fermi paradox. In 1950, physicist Enrico Fermi famously asked, "Where is everybody?" The contradiction lies in the numbers. The universe contains billions of stars, many with planets. Statistically, some of these planets should have life, and some of that life should have advanced far enough to be detectable. Yet in all our searching, across decades of scanning the skies with radio telescopes and probing distant signals, we have heard nothing. No voices from the stars, no evidence of cosmic neighbors. The silence itself is deafening. The paradox has spawned countless theories. Perhaps intelligent civilizations are exceedingly rare, arising only once in unimaginable stretches of time. Perhaps life is common, but intelligence almost never evolves. Another grim possibility is that civilizations rise but inevitably destroy themselves through war, through the collapse of their environment, or through technologies they cannot control before they can reach across the galaxy. It could be that the universe is full of life, but most of it is microbial, forever hidden beneath oceans or soils, never building cities or sending messages. Or maybe advanced civilizations exist but choose to remain silent, watching but never revealing themselves. The possibilities echo like unanswered questions across the cosmos. And so we stand on a quiet planet, shielded by its atmosphere, warmed by its sun, listening to the infinite night. The search for life beyond Earth is not just about discovering microbes on Europa or signals from distant stars. It is about understanding what it means to be alive in a universe so vast and silent. Even the faintest discovery, a single microbe on another world, would change everything. It would mean Earth is not unique. It would mean life is written into the fabric of the cosmos. And if life is written there, then perhaps intelligence, perhaps even companionship is too. The question is no longer only whether we are alone, but what silence itself is telling us. One of the most vital treasures Earth gives to every form of life is its atmosphere. This invisible yet powerful blanket surrounds the planet, performing a symphony of roles that sustain existence. It shields us from lethal radiation streaming in from the depths of space, radiation that would otherwise scorch the surface and annihilate living organisms. It traps heat, acting as a regulator that keeps temperatures from swinging wildly between extremes. It stands as a guardian against the relentless solar wind, a stream of charged particles rushing outward from the sun that could strip a planet bare. Without this fragile yet resilient layer, Earth would be nothing more than a frozen, airless wasteland, bombarded endlessly by cosmic fire, a place utterly hostile to life. Now consider what it would take for another world to bear life. To harbor creatures of any kind, a planet must weave together the same intricate protections Earth provides. It would need an atmosphere capable of absorbing deadly rays, a mechanism to balance heat so that the surface does not fry under one sunlit day or freeze into oblivion during the night, and a magnetic shield to deflect the sun's most violent outbursts. These are not luxuries. They are the basic conditions that cradle us. Without them, a planet remains vulnerable to space's harsh indifference, a silent rock adrift in eternal night. This realization leads to a question that captures the imagination of scientists and dreamers alike. Out of the countless planets that orbit countless stars, how many enjoy the same rare harmony that makes Earth habitable? Could there be other worlds where life has sprouted, evolved, and perhaps even become intelligent? In 1961, astronomer Frank Drake attempted to frame this very puzzle with a bold equation. The Drake equation is not a definitive answer, but a framework that dissects the grand question into smaller, approachable pieces. It asks how many stars exist in our galaxy? How many of them have planets? Among those planets, how many lie within habitable zones? Of those, how many foster life? How many forms of life evolve into intelligence? And finally, how many intelligent civilizations reach a stage where they can build technology to send messages into the dark void? The numbers are uncertain, but the process gives scientists a map, a way to organize their search for cosmic company. And yet, a haunting silence fills the sky. If life is as common as the equation suggests, why have we not received so much as a whisper? This riddle is called the Fermi paradox, named after physicist Enrico Fermi, who, in 1950, asked a deceptively simple question: where is everybody? The contradiction is stark. With billions of planets scattered across the Milky Way alone, the odds seem to favor life. But after decades of scanning, no messages, no signals, no signs of civilization have reached us. The emptiness is profound. Speculations abound. Perhaps intelligent civilizations are vanishingly rare, flickering into existence only in rare pockets. Perhaps life arises often, but the climb to intelligence is too steep, leaving most organisms as microbes or simple creatures. Maybe advanced civilizations are their own undoing, destroyed by war, by collapse of ecosystems, or by catastrophic choices long before they can reach across the stars. Others suggest distance itself is the barrier. Even at light speed, signals take centuries or millennia to cross the gulfs of space. A call sent from a distant world may not reach us for ages, or perhaps it has already passed by unnoticed in the cosmic noise. Another theory is that extraterrestrials are here but deliberately silent. Perhaps they avoid us for their protection. Perhaps they watch, detached. Or perhaps they simply do not care to speak to a species still crawling through its infancy. Despite the silence, the search continues. Astronomers and engineers across the planet unite in this quest, wielding radio telescopes the size of mountains, designed to capture faint, narrowband signals that could betray the existence of a distant intelligence. These instruments comb the heavens for patterns that cannot be explained by pulsars, quasars, or the natural chaos of stars. The work is painstaking, but relentless. Though no confirmed signal has been found, technology grows sharper each year, scanning wider swaths of the sky, listening with ever more precision. But the effort to find life is not only about listening, it is also about looking. Missions such as Kepler and TESS have revealed a staggering truth. Planets are not rare at all. They're everywhere. Our galaxy is brimming with them, so numerous that there are likely more planets than stars. Among them are worlds that lie in the habitable zones of their stars, where liquid water could pool and rivers might flow. Every discovery brings us closer to finding a second Earth, a twin world where life could thrive. And while distant planets capture our imagination, some of the most intriguing prospects lie in our own backyard. Within the solar system are icy moons that conceal oceans beneath their frozen shells. Europa, orbiting Jupiter, and Enceladus, circling Saturn, are among the most promising. At first glance, they appear as barren spheres of ice, but beneath their crusts lies liquid water, warmed by the gravitational pull of their giant hosts. These hidden seas could harbor microbial life, perhaps entire ecosystems flourishing in the darkness, far from sunlight, surviving on chemical energy alone. The implications are staggering. If life exists even in our own solar system, then the universe may be teeming with it. If not, then Earth might be rarer than we dare to imagine, a fragile oasis adrift in an ocean of emptiness. Either answer reshapes our place in the cosmos. The search itself, even without definitive results, has already deepened our understanding of the universe and of ourselves. And so humanity listens, humanity watches, humanity wonders. The night sky, ancient and infinite, offers no answers yet, only questions, carried on the silence between stars. However, beneath their frozen shells lies a mystery so profound that it has captured the imagination of scientists and dreamers alike. These worlds, hidden under kilometers of unyielding ice, may not be lifeless wastelands, but instead contain vast and restless oceans, seas of liquid water kept warm by tidal forces and internal heat. To find such places so far from the sun is extraordinary, and yet the very existence of these concealed oceans transforms them into some of the most promising places in the solar system to search for life. Water, the substance that makes our own planet thrive, is the great unifier of biology. Where it flows, even in the harshest environments on Earth, life somehow finds a foothold. Deep beneath Antarctica's glaciers and acidic lakes, inside volcanic vents where temperatures soar, life clings to existence against all odds. If such tenacity is possible here, then why not on Europa or Enceladus, where entire oceans may stretch beneath their icy crusts? Europa, one of Jupiter's largest moons, has long stood at the center of this quest. Its surface is scarred by cracks and ridges, like a shattered window that hints at the ocean below. For decades, scientists have wondered if beneath that surface lies a dark, alien sea teeming with possibilities. Soon, NASA's Europa Clipper will embark on a daring mission to study this enigmatic world. It will fly by Europa dozens of times, scanning its icy shell, measuring its atmosphere, and searching for chemical clues that could betray the presence of life. The mission is not just about exploration. It is about confronting one of the most profound questions humanity has ever asked. Are we alone? What makes Europa's ocean so captivating is its potential similarity to the abyssal depths of Earth. In our own oceans, deep-sea vents pour out superheated water, rich with minerals, and there, in absolute darkness, bizarre creatures flourish. Tube worms, ghostly fish, microscopic organisms, all thriving without sunlight, life drawing energy from chemistry itself. If Earth's deep oceans can sustain such strange and resilient ecosystems, then Europa's hidden sea might be no different. But Europa is not alone in this cosmic story. In 2005, Saturn's moon Enceladus revealed its secret to the Cassini spacecraft. Plumes of water vapor soaring into space from its south pole carried the fingerprints of an ocean beneath the surface. Cassini flew directly through these geysers, tasting them with its instruments, and what it found was astonishing. Water, salts, and organic molecules, the very building blocks of life. In that moment, Enceladus transformed from a distant icy rock into one of the most compelling candidates for extraterrestrial biology. The idea that a hidden sea beneath a small frozen moon could cradle life shook the foundations of planetary science. If life does exist within these distant waters, it would be a revelation. It would mean that biology is not unique to Earth, not a fragile accident of one blue planet, but a natural outcome wherever conditions allow. It would mean that the cosmos itself might be alive in ways we can scarcely imagine. And yet, the fascination with these moons is not only scientific, but philosophical. For in searching the icy darkness of Europa and Enceladus, we are also searching the depths of our own existence. What does it mean to find another form of life? What does it mean if we discover we are not alone? Every discovery, whether it is a plume of vapor, a strange chemical signature, or the possibility of living cells, brings us closer to an answer that humanity has been chasing for millennia. This pursuit connects directly with a far older question, one that predates rockets, telescopes, and even science itself. Long before modern physics, ancient philosophers wrestled with the greatest of all riddles. Why is there something rather than nothing? Over 400 years ago, in the streets of ancient Greece, Parmenides insisted that true nothingness could never exist. For him, existence was eternal, uncreated, and unending. Nothing could not give rise to something because from nothing, nothing comes. His argument was radical, stripping away the idea of a universe born from emptiness and insisting instead on a cosmos without beginning or end. Not all agreed. A century later, Aristotle reimagined the concept. To him, emptiness was not an impossibility, but a kind of potential. He compared it to a blank canvas before the first stroke of paint. It was not truly nothing but a waiting state, filled with the possibility of something. What might look like absence could actually be the foundation for creation. For centuries, thinkers debated these ideas, circling endlessly around the paradox of nothingness. Then, in the 18th century, Immanuel Kant suggested that perhaps the human mind was not even capable of grasping true nothingness. The idea of a complete absence, a reality without matter, space, or time, was so far removed from human experience that perhaps it could not even be imagined. To Kant, the very act of conceiving nothing revealed its impossibility. But in the 20th century, science shattered the old notions of emptiness. Where philosophers saw paradoxes, physicists discovered phenomena. Space, once thought to be a vacuum devoid of substance, revealed itself to be alive with hidden energy. Einstein's theory of general relativity showed that space and time are not separate, but form a fabric that bends and stretches in response to matter. Space was no longer an empty stage, but an actor in the cosmic play. Then came quantum mechanics, which revealed an even stranger truth. In the tiniest scales of reality, empty space is never truly empty. Instead, it is alive with quantum fluctuations, bursts of energy that flicker into existence and vanish in an instant. Invisible particles called virtual particles appear and disappear constantly, leaving faint traces of their presence. This meant that even the purest vacuum was not silence, but a restless hum of activity. If emptiness itself is pregnant with possibility, then the line between nothing and something begins to blur. Out of these fluctuations, energy can erupt, and from energy, the seeds of creation may grow. This has led many scientists to a breathtaking idea, that the universe itself may have begun from a quantum fluctuation, a ripple in the apparent nothingness that blossomed into everything. The Big Bang, the colossal event that gave birth to space, time, and matter, may not have required a cause in the traditional sense. It may have arisen from the natural laws of physics themselves. Thinkers like Stephen Hawking and Lawrence Krauss have argued that the universe could emerge spontaneously from quantum fluctuations. In this view, there was never true nothingness. What looked like emptiness was filled with quantum potential, a cosmic seed waiting to burst into reality. Imagine the scene. No stars, no galaxies, no light, no space, not even time. Then, in an instant, a spark of energy appears, not placed by hand, not lit by a divine match, but simply arising from the laws of physics themselves. That spark grows, expands, and unfolds into the universe, our universe, with its countless galaxies, suns, and worlds. If this is true, then nothingness is not the absence of being, but the fertile soil of existence itself. What we call nothing may in fact be the very fabric that gives rise to everything. The icy oceans of Europa and Enceladus, the paradoxes of ancient philosophy, the quantum vacuum seething with energy, all are threads in a single boundless tapestry. And so the search continues, both out there among the stars and within the deepest recesses of human thought. Whether it is through a spacecraft diving through Enceladus's plumes, or a physicist studying the vacuum of space, or a philosopher questioning the essence of reality, the same truth emerges. We are seekers in a vast cosmos, forever asking, forever wondering, what does it mean to exist, and can nothing ever truly be? The concept of nothing has captivated human thought for millennia, a profound enigma that has pulled philosophers, mystics, and scientists alike into its dizzying orbit. For ages, nothing was imagined as a void, a barren expanse, utterly devoid of life, energy, or movement. People pictured it as a blandness, a vast emptiness stretching infinitely, where absolutely nothing occurred. Yet, as our understanding deepened, it became clear that nothing is far from simple. It is a concept layered with paradox, a territory where emptiness and potential collide in ways that defy intuition. Philosophers long ago began to explore the hidden dimensions of nothing, proposing that beneath the apparent emptiness lies latent possibility. What seems absent of substance may in fact be brimming with potential, like an invisible reservoir awaiting the spark of creation. Nothing, in this view, is not a void but a stage upon which the universe might emerge. This philosophical insight finds an astonishing echo in the realm of modern physics. Quantum mechanics, the science of the very small, reveals that even the emptiest stretches of space are teeming with invisible activity. Tiny fluctuations, ephemeral bursts of energy, flicker in and out of existence, their collective power sufficient to spark entire universes into being. Space that seems utterly vacant is, in truth, pregnant with the raw material of creation. Imagine for a moment that what we perceive as absolute emptiness is actually a cosmic womb, containing the capacity for galaxies, stars, planets, and life itself. What once seemed barren is instead the birthplace of everything. Philosophers and scientists alike marvel at this, acknowledging that the true nature of nothing might forever elude human comprehension. Yet the fascination endures because it touches the deepest questions of existence, the origins of all matter, energy, and life, the story of the universe itself. From the contemplative musings of ancient Greeks to the meticulous observations of modern laboratories, the journey to understand nothing has spanned civilizations, cultures, and centuries. Standing beneath the night sky with billions of stars scattered across the dark canvas of space, it becomes almost humbling to consider that such grandeur could have arisen from apparent emptiness. The galaxies swirling above, the brilliant sparks of distant suns, the planets orbiting in delicate cosmic dance, all may have originated from a state of nothingness so extreme that our minds strain to grasp it. The universe itself could be the result of what we once thought of as absolute void, a testament to the power of potential hidden in emptiness. At the heart of this mystery lies one of modern science's most confounding concepts, the singularity. This point at the very core of the Big Bang is believed to have contained all matter, energy, space, and time in an infinitely compressed state. The singularity is a paradox, a region where gravity becomes incomprehensibly strong, matter collapses into a point of infinite density, and the familiar rules of physics cease to apply. Time itself, as we understand it, is entwined with space into a single continuum called space-time. If space-time itself was born in the Big Bang, then asking what preceded it may be meaningless. The very concept of before may have no place in such a reality. Yet scientists push the boundaries of imagination, proposing daring theories to explore what might lie beyond this cosmic beginning. Some envision a cyclic universe, endlessly expanding and contracting in a rhythm of creation and collapse, each cycle birthing a new Big Bang. In this framework, our current universe is merely the latest iteration of an eternal cosmic rhythm. Others turn to quantum mechanics, where particles and energy fluctuate unpredictably in otherwise empty space. From such fluctuations, some theorists suggest our universe itself could have spontaneously emerged, a random spark igniting the cosmos. Even more radically, multiverse theory suggests that countless universes coexist, each with its own laws, properties, and destinies. In this vision, our universe is neither first nor last. It is simply one among an infinite sea of realities. Before the Big Bang, there may have existed other universes, other realms of existence beyond our comprehension, an eternal tapestry of possibility. Groundbreaking work by physicists such as Stephen Hawking and Roger Penrose further deepened our understanding of singularities. By uniting Einstein's general relativity with quantum mechanics, they revealed that singularities are not abstract concepts, but real conditions where our familiar physics collapses entirely. Rewinding the universe to its very beginning, we encounter a state where space bends infinitely, time halts, and conventional understanding disintegrates. Before the Big Bang, there was no clock ticking, no expanse to traverse, only a realm of infinite density, a prelude to creation itself. Science has illuminated the unfolding of the universe after the Big Bang in dazzling detail, tracing the formation of galaxies, stars, and planets. Yet the origin remains profoundly mysterious. If time itself began at that moment, the question of what came before may forever elude definitive answer. And perhaps that is the most striking truth of all. Nothing, in its enigmatic depth, is not merely the absence of something, but the canvas upon which everything, every star, every planet, every life form has come to be. It is the silent, invisible stage from which the universe leaps into existence, a reminder that the greatest story of all may indeed begin with nothing at all. However, countless scientists contend that the true laws of physics required to explain the universe's origins remain undiscovered, hidden just beyond the reach of current human understanding. In our daily lives, time appears linear, an unstoppable river flowing endlessly from one moment to the next. We instinctively measure life in units of before and after, yesterday, last year, millennia past. Yet when we attempt to apply this logic to the universe's birth, our intuitive notions crumble. At the very heart of this cosmic enigma lies the singularity, a point where all familiar physical laws collapse and cease to function. Some researchers suggest that time itself was born with the Big Bang, meaning that asking what occurred before it is a meaningless question, like seeking a path beyond the North Pole, a place with no further direction. From this perspective, time is confined within our universe, having no existence prior to its creation. But not all scientists agree. Some hypothesize that the singularity may not have marked the ultimate beginning, but rather emerged from a pre-existing reality. One compelling theory posits that the universe could have spontaneously arisen from tiny, unpredictable bursts of energy in a void of nothingness, random fluctuations that somehow sparked the genesis of all matter and energy. Another proposes that our universe is merely one in an endless cosmic cycle, each universe collapsing in on itself and giving rise to the next, a perpetual chain of creation and destruction. Though speculative and uncertain, these concepts stretch human imagination and hint at realms beyond observable reality. Among those who grappled with these mysteries, Stephen Hawking stands as a monumental figure. He devoted decades to probing black holes, cosmic regions of gravity so intense that not even light can escape. The core of a black hole contains a singularity, echoing the conditions theorized at the universe's birth. By studying these extreme objects, scientists aim to unlock secrets of existence's earliest moments. In one groundbreaking revelation, Hawking discovered that black holes are not entirely black. They emit faint radiation, now known as Hawking radiation. This unexpected finding implied that black holes could gradually shrink and ultimately vanish, prompting profound questions. What becomes of the information they once contained? Does it vanish forever, or is there an unknown mechanism preserving it? These questions challenge the very foundations of physics and our understanding of reality. The study of singularities, whether at black holes or the universe's origin, highlights a deep fissure in modern science. Einstein's general relativity, which explains gravity and the behavior of massive objects, and quantum mechanics, which governs the subatomic realm, cannot currently be reconciled. In the extreme environment of a singularity, both theories falter, revealing a gap in comprehension that physicists have long sought to bridge. Many believe that the solution lies in quantum gravity, a hypothetical framework that would unify relativity and quantum mechanics. Discovering such a theory could illuminate the mysteries of black holes, the Big Bang, and even the possibility of existence prior to the universe's birth. Decades of effort have produced sophisticated models, intricate mathematics, and countless hypotheses, yet the behavior of gravity on the quantum scale remains elusive. This gap is more than academic. It blocks our understanding of the singularity, the very moment when space, time, and matter emerged. The singularity is not just the universe's starting point, it is a boundary of knowledge, a cosmic wall that science has yet to penetrate. Everyday experience conditions us to see the world as predictable. Causes produce effects, space is three-dimensional, time flows forward like an arrow. The singularity shatters these assumptions, forcing a confrontation with the unimaginable. Could it be that the laws of physics themselves only came into existence after the Big Bang? Might time, as we perceive it, have no meaning before that instant? These questions lead into humanity's oldest and deepest contemplations. What does it mean to exist? How can something arise from nothing? Can the exact moment of the universe's birth ever be fully comprehended? For millennia, philosophers and scientists alike have wrestled with these mysteries, and they continue to inspire exploration today. Advances in technology push these boundaries ever further. Telescopes peer deeper into the cosmos, particle colliders probe the smallest constituents of matter, and theoretical frameworks strive to unify the cosmic and the quantum. Yet the singularity remains an enigma, a riddle compelling humanity to stretch intellect and imagination beyond familiar limits, offering both an invitation and a challenge to confront the universe's deepest secrets. Dark matter represents another profound cosmic puzzle. This invisible, enigmatic substance neither emits nor reflects light and does not interact with radiation, making it undetectable by conventional means. Its existence is inferred from its gravitational effects. Galaxies rotate and cluster in ways inconsistent with the mass we can see. Dark matter shapes galactic structures, bends light through gravitational lensing, and influences the cosmic microwave background, the faint afterglow of the Big Bang. According to the lambda cold dark matter model, all matter and energy in the universe fall into three categories. Ordinary matter, which comprises stars, planets, and people, amounts to only 5%. Dark matter constitutes approximately 26.8%, and dark energy, a mysterious force driving cosmic acceleration, makes up 68.2%. Together, dark matter and dark energy account for roughly 95% of all existence. Despite its pervasive influence, dark matter remains elusive. It interacts with ordinary matter only through gravity, making direct detection extraordinarily difficult. Leading theories propose it consists of unknown particles such as weakly interacting massive particles, or WIMPs and axions, or perhaps ancient primordial black holes. Scientists also categorize dark matter by particle velocity, hot, warm, or cold. Most evidence favors cold dark matter, with slowly moving particles capable of clustering to form galaxies and galactic networks over billions of years. While widely accepted, some researchers challenge dark matter's existence, proposing that the anomalous cosmic phenomena might reflect flaws in our understanding of gravity itself. Alternative models, including modified Newtonian dynamics, suggest that gravity may behave differently on vast cosmic scales. This interplay of singularities, black holes, and dark matter underscores humanity's ongoing confrontation with the unknown. Each discovery peels back a layer of cosmic mystery while simultaneously exposing deeper, more perplexing questions. The universe remains an immense, enigmatic theater, where the most familiar concepts, time, space, matter, and energy, reveal themselves as fragile constructs, challenged by extremes beyond comprehension and beckoning us toward ever greater understanding. However, none of the alternative ideas could fully account for all the observational evidence. While some theorists speculated that our understanding of gravity might require subtle adjustments, dark matter remained the indispensable missing piece in the cosmic puzzle. The concept of dark matter has a history stretching back more than a century, a story woven with brilliant minds, unexpected observations, and groundbreaking theoretical leaps. The tale begins in the late 19th century when astronomers first noticed peculiar patterns in the motion of stars and galaxies. In the year 1884, a Scottish physicist named William Thomson, better known to the world as Lord Kelvin, made a remarkable observation. He was meticulously studying the stars surrounding our sun, attempting to estimate how densely they were packed within the local stellar neighborhood. By analyzing their motions, he concluded that if there were about 1 billion stars within a region extending 1 kiloparsec, roughly 3,260 light years, their velocities could not be explained by the visible matter alone. Though Kelvin never used the term dark matter, his insights laid the crucial groundwork for generations of future researchers. At the same time, he estimated the sun's age to lie somewhere between 20 and 100 million years, a figure we now know to be vastly too small. Nevertheless, his relentless curiosity about the hidden forces of the cosmos opened the door to entirely new realms of inquiry. Fast forward to the year 1960, when the French mathematician and physicist Henri Poincaré brought the discussion forward. Reviewing Kelvin's work, he proposed that unseen mass might permeate the universe, although he considered it less significant than the ordinary matter we could observe. He coined the term matière obscure, or dark matter, giving the concept a name and propelling into mainstream scientific dialogue, even though his quantitative estimates were far from precise. In the early 20th century, more astronomers became fascinated by the invisible scaffolding that might shape the universe. In 1922, the Dutch astronomer Jacobus Kapteyn studied stellar motions and found discrepancies between expected velocities and those predicted by the visible mass alone. This marked one of the earliest indirect hints of dark matter. A few years later, in 1930, Swedish astronomer Knut Lundmark observed that galaxies seemed far heavier than the stars, gas, and dust visible through telescopes could account for, suggesting the existence of vast reservoirs of hidden matter. In 1932, another Dutch astronomer, Jan Oort, examined stellar motion within the Milky Way. He discovered that the galaxy's mass appeared far greater than what was visible, leading him to propose the presence of invisible material contributing extra gravitational weight. Later research revealed that Oort's measurements were not entirely precise, indicating that further study was required to understand the true nature of this unseen matter. The year 1933 marked a pivotal moment when Swiss astrophysicist Fritz Zwicky, studying clusters of galaxies at the California Institute of Technology, noticed something extraordinary. While examining the Coma cluster, he found that galaxies were moving at velocities far exceeding what visible matter could account for. He deduced that an enormous amount of invisible mass must be exerting gravitational influence to keep these galaxies bound. Zwicky estimated that the Coma cluster's total mass was about 400 times greater than what telescopes could detect, naming this hidden substance Dunkel Materie, or dark matter. Though his calculations contained errors due to outdated assumptions, he was one of the first to recognize that an unseen force governed galactic motion. Unlike today's understanding, Zwicky believed this dark matter was ordinary matter that emitted no light, rather than a mysterious new form of matter. His pioneering work nevertheless laid a crucial foundation for decades of research. By the late 1930s, additional evidence emerged. In 1939, astronomer Horace W. Babcock studied star motion in the Andromeda Galaxy, the nearest spiral galaxy to our own. He discovered that stars at the galaxy's outer edges moved far faster than expected, implying the presence of mass far beyond the visible components. Initially, Babcock speculated that interstellar absorption or structural changes in the galaxy could explain these anomalies, but in reality, his observations hinted at a massive invisible influence shaping rotation. The following year, 1940, astronomer Jan Oort examined galaxy NGC 3115 and discovered a vast unseen halo of mass enveloping it, further reinforcing the notion that galaxies contain far more matter than could be directly observed. The 70s brought a dramatic shift in cosmic perspective. By 1974, two independent research groups reached the same startling conclusion. Galaxies are embedded in enormous, invisible halos of matter. One team in Princeton, New Jersey, included Jeremiah Ostreicher, Jim Peebles, and Amos Yehiel, while the other, based in Tartu, Estonia, was led by John Einasto and colleagues. Their converging findings solidified the emerging picture of dark matter as a fundamental cosmic component. One of the most compelling pieces of evidence came from studying galactic rotation. Astronomers employed both optical and radio telescopes to track the motion of stars, and gas. Vera Rubin and Kent Ford, using the spectrograph, measured stellar velocities across spiral galaxies with unprecedented precision. They discovered a startling truth. Stars near the galactic edges moved as fast as those near the center, defying expectations based on visible mass. Simultaneously, radio astronomers studied the 21-centimeter wavelength emission of atomic hydrogen, observing gas motion far beyond the regions of visible stars. These observations extended the known rotation curves, revealing that the outer regions of galaxies maintained high velocities, contrary to the predictions of Keplerian motion, which dictates that speed should decrease with distance from the center. By 1975, astronomers Roberts and Whitehurst extended the Andromeda rotation curve to a staggering 30 kiloparsecs. Their analysis confirmed that even at these extreme distances, the galaxy's rotation remained unexpectedly rapid, necessitating vast reservoirs of unseen mass exerting gravitational influence. Advanced techniques such as interferometry, used by Rogstad and Shostak in 1972, further revealed similar rotation patterns in multiple spiral galaxies, underscoring the universality of these invisible halos. By the late 70s, dark matter had transitioned from a speculative hypothesis to a central mystery in astronomy. Scientists recognized that this enigmatic substance was not confined to individual galaxies but likely permeated the cosmos itself. From 1980 through 1999, a continuous stream of observations and measurements strengthened the case for dark matter, establishing it as one of the most profound and enduring enigmas in our understanding of the universe. One of the most groundbreaking investigations into the hidden architecture of the cosmos unfolded in 1996, when researchers Persic, Saluki, and Stell undertook a meticulous survey of 967 spiral galaxies. What they uncovered sent shockwaves through the scientific community, compelling evidence that an invisible yet immensely massive force was guiding the motion of these galaxies in ways that could not be explained by the matter we can see. This revelation was just the beginning. Soon, additional lines of evidence began to accumulate. Astronomers observed a phenomenon known as gravitational lensing, where massive clusters of galaxies functioned as cosmic magnifying glasses, bending the light from objects lying far behind them. They examined the distribution of hot gas within galaxies and clusters, noting the patterns of temperature it exhibited. They studied the cosmic microwave background, the faint afterglow of the Big Bang itself, and detected subtle irregularities that suggested unseen forces at play. Every new observation pointed in the same direction. A mysterious hidden form of matter was sculpting the structure of the universe. Today, the vast majority of physicists agree that this invisible entity, dark matter, is composed of particles entirely unlike any we have previously discovered. These elusive particles have become one of the most formidable mysteries in modern physics. Around the globe, scientists deploy cutting-edge detectors and massive experimental apparatuses, hoping to glimpse these particles and reveal the truth of what dark matter truly is. To grasp dark matter, it helps first to understand how different forms of energy behave across the expanding universe. Ordinary matter, including stars, planets, and galaxies, disperses as space itself stretches. Its density diminishes predictably, decreasing in proportion to the cube of the universe's expansion. This means that as the cosmos grows, matter becomes increasingly diffuse. Radiation, including light and cosmic rays, thins even faster, obeying a rule called the inverse fourth power of expansion, so its energy diminishes far more rapidly as space expands. Yet there is an anomaly known as the cosmological constant, a form of energy that behaves entirely differently. Its energy density remains constant, regardless of how vast the universe becomes. This distinction arises from a phenomenon called radiation redshift. Imagine the universe expanding like a balloon being blown up. If the universe doubles in size, the wavelengths of radiation stretching through it also double, causing their energy to drop. Light from the cosmic microwave background and tiny, fast-moving early neutrinos both lose energy in this process. But the cosmological constant is a property of space itself. immune to expansion, its energy unchanged no matter how vast the universe grows. Dark matter refers to the invisible mass pervading the universe, a substance that emits no light and eludes direct detection. Scientists use the term specifically for a type of matter that is not made of familiar particles like protons and neutrons, which constitute ordinary baryonic matter. Unlike these missing baryons, dark matter cannot be observed directly. Its existence must be inferred from the gravitational effects it produces. One of the clearest hints of dark matter comes from the rotation of spiral galaxies. In our solar system, planets near the sun orbit rapidly, while those farther away move slowly, following Kepler's third law. But when astronomers measured the rotation speeds of stars in galaxies, they discovered something astonishing. Stars at the outer edges move just as quickly as those near the center. This should be impossible if only visible matter were present. The only plausible explanation is that a vast quantity of unseen mass permeates the galaxy, providing the extra gravitational pull needed to maintain these high velocities. This invisible scaffolding is what we call dark matter. The distribution of mass in galaxies also follows the virial theorem, a principle that allows astronomers to estimate a system's total mass based on the motion of its stars. When applied to elliptical galaxies and dense star clusters, the results were puzzling. The observed velocities did not match the mass of visible matter, even after accounting for complex stellar orbits. Again, the simplest explanation pointed to a hidden mass, dark matter, lurking unseen. Galaxy clusters offer another powerful method for measuring dark matter. Scientists rely on three primary approaches. First, they examine the velocities of galaxies within a cluster. If only visible matter were present, galaxies would move far more slowly. The high speeds observed indicate the presence of additional invisible mass binding the cluster together. Second, astronomers measure the X-rays emitted by hot gas in these clusters. By calculating the gas's temperature and density, they determine the pressure, which, when balanced against gravity, reveals the total mass. In every case, the mass inferred far exceeds what is visible. Third, they exploit gravitational lensing, the bending of light from background objects by the cluster's immense gravity. By analyzing the distortions of light, scientists can calculate the cluster's total mass, independent of galaxy motions. All three methods converge on the same conclusion. Dark matter exists and outweighs ordinary matter by roughly 5-to-1, forming a hidden framework essential to the structure of galaxies, clusters, and the universe itself. Gravitational lensing, a concept arising from Einstein's theory of general relativity, is particularly captivating. When a massive object such as a galaxy or cluster lies between a distant light source and an observer on Earth, it acts as a cosmic magnifying glass, bending and distorting the light traveling through space. The result can be a dramatic stretching, duplication, or warping of the background object's appearance. This effect depends solely on mass, not its composition. The heavier the object, the more it bends light. There are two primary manifestations of lensing. Strong lensing occurs when light from distant galaxies is stretched into bright, arc-like shapes. Observations of clusters like AEL 1689 have allowed scientists to estimate the mass of these clusters by analyzing the arcs. Weak lensing, by contrast, is subtler. Galaxies do not form arcs, but experience slight stretching or skewing. Even these tiny distortions are invaluable, allowing researchers to map the distribution of dark matter across the cosmos. Observations of both strong and weak lensing consistently align with theoretical predictions, reinforcing our understanding of dark matter's pervasive presence. In the early universe, ordinary matter carried electric charge, which meant it interacted with light and was constantly jostled by radiation. This interaction prevented it from clumping together efficiently. Dark matter, on the other hand, interacts only gravitationally, allowing it to form the invisible skeleton of the universe, shaping galaxies and clusters long before ordinary matter could catch up. It is this silent architect, invisible yet indispensable, that underpins the vast cosmic tapestry we see today. One of the most profound ways dark matter asserts its invisible presence is through its influence on the cosmic microwave background, often abbreviated as CMBB. This faint, ghostly glow is the lingering radiation from the universe's fiery birth in the Big Bang, a relic light that has traveled across more than 13 billion years of cosmic history. Dark matter, invisible to telescopes yet massive in effect, exerts gravitational forces that subtly guide how ordinary matter clumps and flows. These gravitational nudges leave behind delicate, almost imperceptible imprints in this primordial radiation, patterns that scientists can now read like the universe's earliest diary. The CMBB is astonishingly uniform, with temperature variations so minuscule that they differ by only 1 part in 100,000. Yet these tiny ripples, known as anisotropies, carry an extraordinary wealth of information about the universe's infancy. By mapping these anisotropies across the sky and translating them into graphs called angular power spectra, researchers uncover a sequence of peaks and valleys, each peak revealing critical insights into the universe's makeup, its geometry, and its ultimate fate. The first detection of these minute variations came in 1992 with the COBE satellite, an achievement that transformed cosmology. COBE confirmed that the early universe was not perfectly smooth, but had subtle fluctuations, though it lacked the precision to capture the detailed structure of the peaks. By the year 2000, high-altitude balloon experiments like Boomerang provided the first sharp measurements of these peaks, setting the stage for space missions such as WMAP and Planck. These observatories supplied extraordinarily precise maps of the CMBB, confirming that the large-scale structure of the cosmos aligns remarkably well with the lambda CDM model, the cornerstone theory of modern cosmology. In the aftermath of the Big Bang, the universe was a vast, almost uniform expanse of particles, a cosmic sea without stars or galaxies, where energy and matter were evenly spread. Yet even in this nearly homogeneous expanse, tiny irregularities in density existed. Over time, these small differences amplified under the relentless pull of gravity, initiating a process called structure formation. Minute density variations gradually accumulated matter, creating galaxies, clusters, and sprawling cosmic superstructures. During these earliest moments, radiation dominated over matter, its immense energy preventing ordinary matter from coalescing. Had the universe consisted solely of visible matter, there would have been insufficient time for galaxies to form. The solution lies in dark matter. Unlike ordinary matter, dark matter does not interact with radiation, allowing it to collapse into dense regions ahead of ordinary matter. These invisible scaffolds formed gravitational wells that later drew in normal matter, setting the stage for the birth of galaxies. In essence, dark matter provided the unseen framework upon which all cosmic architecture rests. One of the most dramatic pieces of evidence for dark matter emerges from the Bullet Cluster, a system created by the collision of 2 colossal galaxy clusters. When astronomers used gravitational lensing to chart the distribution of mass within this system, they discovered a startling separation. Most of the mass did not coincide with the visible galaxies or hot gas. This observation directly challenges alternative gravity theories, which predict that gravitational effects should trace visible matter alone. The standard dark matter model, however, accounts for it perfectly. During the collision, ordinary matter, primarily in the form of hot gas, interacted electromagnetically, slowing down and remaining near the center, while dark matter passed through almost unaffected. Gravitational lensing revealed 2 distinct peaks in mass, one associated with visible matter, the other with dark matter. This clear separation confirmed that dark matter is a distinct, tangible component of the universe, invisible, yet overwhelmingly influential. In addition to dark matter, scientists probed the universe for another mysterious entity, dark energy. One of the most precise methods to gauge the universe's expansion involves Type Ia supernovae, exploding stars that shine with a predictable brightness. By comparing their known luminosity to how faint they appear from Earth, astronomers can estimate their distance. Observations of these cosmic beacons revealed a startling truth. The universe's expansion is accelerating. This rapid, unexpected expansion is attributed to dark energy, an enigmatic force that constitutes roughly 70% of the cosmos. Equally fascinating are baryon acoustic oscillations, or BAO. Imagine the early universe as an extremely hot, dense soup of particles and radiation more than 13 billion years ago. Sound waves propagated through this cosmic plasma, compressing and rarefying matter in rhythmic patterns. Once the universe cooled sufficiently for atoms to form, these waves froze in place, leaving subtle yet measurable ripples in the distribution of galaxies. Even today, galaxies show a slight preference for separations around 147 million light-years, an echo of these primordial waves. Predicted in the 1990s and confirmed by massive surveys such as the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey in 2005, these ripples, together with the CMBB, provide critical constraints on the universe's expansion rate and matter content. Mapping the cosmos on a grand scale relies on galaxy redshift surveys. Redshift, the stretching of light from distant galaxies due to cosmic expansion, allows scientists to track the universe's growth. Yet redshift is not simple. It has two components. The dominant factor reflects the expansion of space itself, but galaxies also move due to local gravitational forces, a motion called peculiar velocity. This interplay creates a cosmic tug-of-war. Massive superclusters exert gravitational pulls that slightly retard the expansion of nearby galaxies, while enormous voids, vast empty regions of space, expand more rapidly than the average. As a result, galaxies near superclusters display distorted redshifts. Those in front appear to move faster, those behind slower, creating the illusion that superclusters are squashed and voids stretched. These distortions are a subtle but telling signature of the universe's underlying structure and the invisible hand of gravity shaping it. Through the careful study of the cosmic microwave background, baryon acoustic oscillations, type Ia supernova, and the gravitational choreography of galaxies, scientists have built an intricate and awe-inspiring picture of our universe. Dark matter provides the scaffolding, dark energy drives the expansion, and the traces of sound waves from the infant cosmos remain etched in the distribution of galaxies. Together, these discoveries converge to support the lambda CDM model, a framework that, despite its invisible components, continues to illuminate the profound dynamics of the cosmos. However, because the precise shapes of individual superclusters remain unknown, detecting their subtle influences by examining just one is nearly impossible. Instead, astronomers turn to statistical methods, observing vast numbers of superclusters and cosmic voids, then averaging their measurements to uncover hidden patterns etched across the universe. This remarkable phenomenon was first theorized by physicist Nick Kaiser in 1987. And it took more than a decade before observational evidence confirmed his predictions. In 2001, the 2-degree Field Galaxy Redshift Survey provided the definitive proof, revealing structures and distributions that aligned perfectly with the forecasts of the lambda CDM model, reinforcing our understanding of the large-scale evolution of the cosmos. In a complementary line of research, scientists study the Lyman alpha forest, a complex series of absorption lines imprinted on the light streaming from distant galaxies and quasars. These lines emerge because clouds of neutral hydrogen absorb light at a characteristic wavelength known as the Lyman alpha transition. By analyzing these spectral fingerprints, researchers refine their cosmological models and confirm that their predictions align closely with observations from missions like the Wilkinson Microwave Anisotropy Probe, or WMAP, which maps the faint afterglow of the Big Bang across the sky. Dark matter, one of the most enigmatic components of the universe, is categorized into 3 broad types: cold, warm, and hot. These classifications do not indicate temperature, but rather the speeds at which dark matter particles move during the universe's earliest moments. Central to this concept is the free streaming length, the distance a particle could travel before the expansion of space slowed it down. When compared to the size of a protogalaxy, the nascent structures that eventually grow into fully formed galaxies, this measure determines the classification of dark matter. Particles with free streaming lengths much smaller than a protogalaxy are deemed cold. Those with lengths roughly the same as a protogalaxy are warm, and particles that traveled much farther before slowing down are hot. In the 1990s, some cosmologists theorized that a mixture of these types might explain the universe's structure. However, following the discovery of dark energy, these ideas lost favor. The significance of free streaming length becomes clear when imagining the early universe as a realm dominated by tiny quantum ripples, generating subtle density variations. Over time, particles migrated from denser regions to less dense ones, yet the rapid expansion of space constrained their movement. Hot dark matter particles, moving near light speed, traversed vast distances, while slower, cold dark matter remained close to its origins. These differences profoundly shaped cosmic architecture. If hot dark matter had dominated, massive superclusters would have formed first and later fragmented into galaxies. Observations, however, indicate that galaxies formed first, clustering together into groups, clusters, and superclusters over time, confirming that cold dark matter played the dominant role. Neutrinos, which travel near light speed, exemplify hot dark matter, but they alone cannot account for the observed structure of the universe, reinforcing the necessity of cold dark matter. Despite its invisibility, dark matter exerts a powerful gravitational influence, shaping the motions and formation of galaxies. It may not be entirely alien. Some ordinary matter, including protons, neutrons, and atomic building blocks, interacts gravitationally in ways that resemble dark matter. Objects such as planets, brown dwarfs, red dwarfs, white dwarfs, neutron stars, and even black holes fall under this umbrella. Black holes, for instance, absorb all matter equally, whether it consists of familiar atoms or an unknown form of dark matter, treating it identically once it passes the event horizon. Earlier theories proposed that dark matter might largely consist of these hard-to-detect objects, termed MACOs, short for massive compact halo objects. Over time, however, this hypothesis lost favor as accumulating evidence demonstrated that ordinary matter could not account for the majority of the universe's missing mass. The reasons for this conclusion are manifold. If dark matter were simply hidden gas clouds or dust, they would emit or reflect faint light from surrounding stars. Yet astronomers detect no such glowing structures in the required quantities. Big Bang nucleosynthesis, the process by which elements formed in the early universe, also provides constraints. Were there more ordinary baryonic matter, we would observe larger abundances of helium and lithium than exist. Instead, data indicate that normal matter constitutes only 4 to 5% of the total cosmic inventory, whereas galactic dynamics suggests that around 30% is necessary to explain observed gravitational effects. This discrepancy implies that the majority of matter is invisible, detectable only through its gravitational influence. Gravitational microlensing, a technique that measures how light bends around massive objects, has further demonstrated that known objects like planets, stars, or black holes cannot account for this hidden mass. Observations of the cosmic microwave background, the relic radiation from the Big Bang, provide additional evidence. Data from WMAP and the Planck mission reveal that more than 50% of all matter in the universe is non-baryonic, interacting with ordinary matter primarily through gravity. This strongly suggests that the bulk of dark matter is invisible, revealing itself only through its subtle but pervasive gravitational effects. If ordinary matter cannot account for most of the universe's hidden mass, then dark matter must consist of exotic particles or ancient black holes formed in the earliest moments of cosmic history, long before the first stars. Unlike baryonic matter, these mysterious particles would not have participated in nucleosynthesis, but manifest their presence gravitationally, bending light and warping space in a phenomenon known as weak lensing. Some dark matter candidates, such as weakly interacting massive particles, or WIMPs, might even collide or decay, producing detectable signals including gamma rays or streams of neutrinos. Sophisticated detectors on Earth and in space are actively seeking these signals. WIMPs, if they exist, would behave similarly to familiar fundamental particles, but interact primarily through gravity and, perhaps, the weak nuclear force. They are thought to have formed in the early universe alongside ordinary particles and would constitute cold dark matter, matching observed cosmic structure. To account for the observed abundance of dark matter, WIMPs would need to annihilate at rates consistent with masses near 100 billion electron volts and interactions via the electroweak force, an alignment often called the WIMP miracle, due to its striking compatibility with extensions of the standard model of particle physics. Supersymmetry, a long-standing theoretical framework, predicts stable partner particles, one of which could serve as dark matter. Scientists employ a range of strategies to detect WIMPs, including searching for gamma rays or neutrinos from space, conducting underground experiments to observe collisions with atomic nuclei, and attempting to create them in high-energy colliders such as the Large Hadron Collider. Each of these approaches brings humanity closer to unraveling the enigmatic substance that silently sculpts the cosmos. However, in the early 2010s, the Large Hadron Collider, a monumental experiment designed to probe the deepest secrets of the universe, failed to uncover strong evidence supporting the existence of supersymmetry, a theoretical framework that predicted a host of new particles, including the much-sought WIMPs, or weakly interacting massive particles. This absence of detection casts serious doubt on the simplest WIMP models, leaving physicists to confront the possibility that the nature of dark matter might lie elsewhere. With WIMPs slipping further from reach, attention shifted to an altogether different contender: axions. These particles, nearly massless and ethereal, were first proposed in 1978 by physicists Frank Wilczek and Steven Weinberg, not as a direct answer to dark matter, but as a solution to a thorny issue within quantum chromodynamics, the theory that governs the interactions of quarks and gluons, the building blocks of atomic nuclei. Unlike WIMPs, axions are extraordinarily light, almost ghostly, and interact so weakly with normal matter that detecting them is a Herculean challenge. Yet, despite their subtlety, axions could have been generated in vast quantities in the furnace of the early universe, lingering in enormous numbers to this day. Intriguingly, these enigmatic particles may offer explanations for puzzling, small-scale phenomena that the dominant cosmological framework, the lambda cold dark matter model, struggles to account for. As the search for WIMPs continues without success, the allure of axions grows, fueled by their peculiar quantum properties, which might hold the key to some of the universe's hidden patterns. Another compelling hypothesis posits that dark matter could consist of primordial black holes, cosmic relics, formed not from dying stars, but from dense regions of the universe collapsing under their own gravity shortly after the Big Bang. This scenario suggests black holes predated the birth of the first stars, existing as ancient sentinels in the cosmos. Primordial black holes could range in size dramatically, from the scale of an atom to giants exceeding the mass of ordinary stellar black holes. The idea first emerged in 1967 when physicists Yakov Zeldovich and Igor Novikov proposed that such objects could form in the early universe. And in 1971, Stephen Hawking expanded on this concept, highlighting its potential to solve the enduring enigma of dark matter. Unlike more exotic proposals, primordial black holes carried the appeal of familiarity, grounded in the well-established physics of general relativity, where black holes were already known to exist. If even a fraction of these ancient black holes survived, they might account for dark matter, though their formation requires extreme conditions, such as rapid expansion of space that exceeds standard cosmological predictions. Interest in primordial black holes surged in 2015 when scientists detected gravitational waves, ripples in the fabric of spacetime caused by the collision of black holes. Surprisingly, some of the merging black holes were far more massive than those expected from stellar collapse, hinting they could be primordial in origin. Yet subsequent searches for gravitational lensing, the bending of light by massive but unseen objects, found no evidence of medium-sized primordial black holes scattered throughout the cosmos. This absence did not entirely rule them out. Some researchers argue the assumptions about their mass may have been incorrect. With advanced instruments like the James Webb Space Telescope, astronomers hope to refine these observations, scanning the heavens with unprecedented sensitivity. For a time, tiny primordial black holes were considered capable of constituting a significant portion of dark matter, until data from Voyager 1, as it ventured beyond the influence of the Sun, revealed unexpected patterns in streams of positrons and electrons. The number and energy of these particles were inconsistent with the presence of numerous small primordial black holes, suggesting they were likely too rare to explain dark matter. Despite this setback, theorists continue to explore other dense forms of dark matter, including scenarios where it might cool and condense into compact objects. Observations in 2019 of the Andromeda Galaxy failed to detect microlensing, a phenomenon that would indicate tiny black holes bending light from distant stars, further challenging the primordial black hole hypothesis. Nevertheless, an open gap remains. A mass range too small for current detection methods could still harbor primordial black holes capable of accounting for dark matter. This unresolved question continues to fuel astrophysical research. If dark matter consists of elusive, nearly non-interacting particles, a deeper question emerges. Could they aggregate into objects akin to planets, stars, or even black holes? The prevailing answer has been no, due to two fundamental barriers. Dark matter cannot efficiently shed energy. Ordinary matter collapses into stars and planets because it can radiate energy as light and heat, allowing dense structures to form. Dark matter, interacting primarily through gravity, lacks this mechanism. Particles falling inward simply accelerate and escape, unable to coalesce. Additionally, dark matter does not engage in the rich array of interactions that ordinary matter exhibits, including electromagnetism and nuclear forces. These interactions enable atoms to form, stars to ignite, and galaxies to assemble. Yet dark matter remains limited to gravitational influence alone, incapable of emitting radiation or forming complex structures. Despite these challenges, dark matter, if composed of weakly interacting particles, continuously streams through every square centimeter of Earth, potentially millions or even billions of times per second. Scientists around the world have designed sophisticated experiments, deploying detectors in deep underground laboratories, aiming to capture the fleeting whispers of these ghostly particles, probing the invisible scaffolding that shapes the universe. The quest to illuminate the unseen matter that dominates the cosmos continues, blending theoretical insight, experimental ingenuity, and the profound human desire to understand the hidden architecture of everything around us. One of the most intensely studied candidates for dark matter is a hypothetical particle known as WIMPs, which stands for Weakly Interacting Massive Particles. These elusive entities interact so feebly with ordinary matter that they could pass through entire planets without leaving a trace. But alongside WIMPs, another fascinating contender has been gaining attention in recent years: axions. Axions are ultralight particles that may make up dark matter, and they are the focus of experimental efforts such as the Axion Dark Matter Experiment, or ADMX. Meanwhile, other theoretical models suggest that dark matter might consist of exotic heavy particles residing in a hidden sector of physics, only interacting with the universe we know through the subtle force of gravity. There are two primary experimental approaches aimed at detecting dark matter. Direct detection experiments attempt to catch these shadowy particles in the act, observing them as they collide with atoms in highly sensitive detectors. These instruments are designed to detect the tiniest flashes of energy produced when a dark matter particle strikes a nucleus. Because these interactions are so faint, the experiments are conducted deep underground, shielded from the constant barrage of cosmic radiation. Notable underground laboratories include the Stawell Mine in Australia, the Sudan Mine in the United States, and the Gran Sasso National Laboratory in Italy. Two common detection technologies dominate this field. Cryogenic detectors operate at temperatures near absolute zero and measure minuscule changes in temperature when a dark matter particle collides with materials such as germanium. Noble liquid detectors, on the other hand, use elements like xenon or argon, which emit brief flashes of light when struck by a particle. Among the most advanced experiments are CDMS, CREST, xenon, and LUX, each pushing the boundaries of sensitivity to detect the faintest whispers of these invisible particles. Indirect detection experiments, in contrast, do not try to capture dark matter directly, but instead search for its effects in the cosmos. If dark matter particles can annihilate or decay, they may release gamma rays, positrons, or neutrinos detectable by specialized telescopes. One intriguing observation comes from the Damali experiment, which has recorded an annual fluctuation in its data, possibly hinting at the Earth moving through a cloud of dark matter. Yet, other experiments like LUX and Super CDMS have not confirmed this signal, leaving the mystery unresolved. Directional detection experiments offer another innovative method, tracking the motion of dark matter relative to the solar system as it orbits through the Milky Way. Instruments such as DMTPC and DRIFT aim to identify the incoming direction of dark matter particles, helping distinguish genuine signals from background noise. High-energy telescopes also contribute to the search. If dark matter particles collide, they could release bursts of gamma rays, as suggested by unusual signals detected by the Fermi Gamma Ray Space Telescope from the center of the Milky Way. While some researchers see these as potential evidence of dark matter annihilation, others argue they may be produced by pulsars. The Alpha Magnetic Spectrometer aboard the International Space Station has also reported unexpected excesses of positrons and cosmic rays, hinting at dark matter but leaving the evidence inconclusive. The hunt for dark matter extends even to particle accelerators like the Large Hadron Collider. In high-energy collisions, dark matter particles might be produced, escaping detection and leaving missing energy signatures in their wake. Physicists analyze these gaps in energy to search for hints of the invisible substance. Because dark matter remains unidentified, alternative explanations have emerged. Some propose that gravity itself behaves differently on cosmic scales, potentially eliminating the need for dark matter altogether. Concepts like modified Newtonian dynamics, MOND, and entropic gravity challenge the standard model but struggle to account for the full spectrum of evidence. The universe holds another profound mystery: dark energy, a strange force driving the accelerated expansion of space. It is estimated to comprise about 68% of the total energy content of the cosmos, while dark matter makes up roughly 26%, and all visible matter, stars, planets, and galaxies accounts for just 5%. Other energy forms, such as photons and neutrinos, contribute so minutely they are almost negligible. Despite its extremely low density, about 7 times 10 to the power of negative 30 grams per cubic centimeter, dark energy dominates because, unlike matter, it does not clump but is distributed evenly throughout space. Every cubic centimeter of the universe, from the emptiest void to the heart of a galaxy, contains this pervasive force. The existence of dark energy was first suspected through observations of distant exploding stars called Type Ia supernovae. These stellar explosions act as cosmic mile markers, emitting light with consistent intrinsic brightness. By studying the stretching of their light, a phenomenon known as redshift, scientists can determine how fast these stars are receding. The results were astonishing. Instead of slowing due to the pull of gravity, the universe's expansion was accelerating, revealing the presence of an unknown repulsive force that would later be named dark energy. Several theories attempt to explain its nature. One leading candidate is the cosmological constant, an unchanging energy inherent to empty space, sometimes referred to as vacuum energy. Another possibility involves scalar fields, dynamic energies that evolve over time and space, appearing differently in various regions of the cosmos. These ideas include concepts like quintessence and moduli fields. Some theorists suggest dark energy may interact with gravity in ways we have yet to understand through mechanisms known as cosmological coupling or interacting dark energy. Interestingly, the concept of a cosmic energy permeating space dates back to Albert Einstein. In the early 20th century, Einstein introduced the cosmological constant, denoted by lambda, in his equations of general relativity. At that time, he assumed a static universe, neither expanding nor contracting, and the constant served as a force counteracting gravity. However, in 1929, Edwin Hubble discovered that the universe was indeed expanding, prompting Einstein to call the constant his greatest blunder. Ironically, decades later, the notion of dark energy showed that the universe was, in fact, dominated by a repulsive force, suggesting Einstein's intuition was not entirely mistaken. In the 1980s, physicists Alan Guth and Alexei Starobinsky introduced the theory of cosmic inflation, proposing that the universe underwent an extremely rapid expansion immediately after the Big Bang. This inflationary period shaped the large-scale structure of the cosmos and explains the distribution of galaxies we see today. While inflation shares similarities with dark energy, the energy driving inflation was far stronger, and scientists continue to investigate whether the two phenomena are linked or entirely distinct. By the 1980s, models incorporating cold dark matter, or CDM, which moves slowly compared to the speed of light, had become central to understanding cosmic evolution. These models successfully explained the formation of galaxies, but predicted slower expansion rates than observed. In 1992, NASA's COBE spacecraft revealed subtle irregularities in the cosmic microwave background, the faint afterglow of the Big Bang, prompting a reevaluation of cosmological models. A watershed moment came in 1998 when observations of distant supernova provided unambiguous evidence that the universe's expansion was accelerating, offering the first direct confirmation of dark energy. Subsequent studies, such as the Boomerang and Maxima experiments in the early 2000s, further mapped the cosmic microwave background, demonstrating that the total energy density of the universe closely matches the critical density, the precise amount needed for the cosmos to be geometrically flat on large scales. The hunt to understand dark matter and dark energy continues, revealing an ever-deepening tapestry of the universe, where unseen forces shape the fate of galaxies, stars, and the very fabric of space itself. However, when astronomers and physicists meticulously measured the total amount of matter in the universe, they encountered a startling revelation. All the visible and dark matter combined accounted for only about 30% of what is known as the critical density, the precise balance required to shape the geometry of the cosmos. The remaining 70% was not immediately identifiable, and this deficit led scientists to propose the existence of a mysterious pervasive force now called dark energy. Subsequent evidence supporting this notion emerged from the 2-degree field, or 2DF, Galaxy Redshift survey conducted in 2001. By mapping the positions and movements of hundreds of thousands of galaxies across the sky, this survey revealed patterns that could not be explained solely by matter alone, pointing directly to the influence of an unknown energy permeating space. Between 2003 and 2010, the Wilkinson Microwave Anisotropy Probe, better known as NASA's WMAP satellite, provided an even more precise and comprehensive map of the cosmic microwave background, the faint afterglow of the Big Bang. These measurements allowed researchers to refine models of the universe's structure and history, solidifying the so-called lambda cold dark matter, or lambda CDM, model as the prevailing framework for explaining how the cosmos evolves. The term dark energy itself was first coined in 1998 by physicist Michael S. Turner, building on the concept of dark matter, a phrase introduced decades earlier by Fritz Zwicky in the 1930s when he noticed galaxies moving as though influenced by unseen mass. Despite decades of study, dark energy remains one of the most profound enigmas in physics. Some scientists speculate it might be an intrinsic property of space itself, while others believe it could arise from quantum mechanics, the counterintuitive principles that govern the behavior of particles at subatomic scales. Ongoing and future observational campaigns, including advanced space telescopes and expansive galaxy surveys, are designed to shed light on this elusive phenomenon. To understand how the universe expands and stretches over billions of years, researchers must make measurements of extraordinary precision. Within the framework of Einstein's general relativity, the expansion rate of the universe is deduced not just from observing galaxies, but by analyzing the shape of space and a pivotal concept known as the cosmological equation of state. This equation describes how factors such as temperature, pressure, and the densities of matter, energy, and vacuum interact across the cosmos. One of the most significant challenges in cosmology today is determining the precise equation of state for dark energy, a force believed to be the main driver of the universe's accelerated expansion. To study its effects, scientists include a term called the cosmological constant in their standard cosmological model, formalized through the Friedmann-Lemaitre-Robertson-Walker metric. This formulation underpins the lambda CDM model, often hailed as the gold standard of cosmology because it accurately reproduces observations from the universe on both large and small scales. Since 2013, this model has been repeatedly validated through extraordinarily precise datasets, including observations from the Planck spacecraft and the Supernova Legacy Survey. Early results suggested that dark energy behaves nearly identically to the predictions made by Einstein's cosmological constant, with a precision of roughly 10%. More recently, data from the Hubble Space Telescope's Higher-Z team revealed that dark energy has influenced the universe for at least 9 billion years, predating the onset of rapid cosmic acceleration. Despite these advances, dark energy remains profoundly mysterious. It is astonishingly uniform, spread evenly across space, and possesses an extraordinarily low density, roughly 1 part in 10 followed by 27 kilograms per cubic meter, a quantity far too small to be detected in conventional laboratory experiments. Yet it constitutes nearly 70% of the total energy content of the cosmos. Unlike ordinary matter, which clumps together under gravity, dark energy maintains a constant presence, gently but relentlessly driving the universe's expansion. One leading hypothesis ties dark energy to vacuum energy, arising from the fleeting creation and annihilation of particle-antiparticle pairs in otherwise empty space, as dictated by Heisenberg's uncertainty principle. According to relativity, this vacuum energy exerts a gravitational effect, contributing to the cosmological constant and thereby accelerating the expansion of space itself. A major theoretical problem arises when quantum field theory is applied to calculate the expected vacuum energy. The predicted value is staggeringly larger than what is observed, presenting one of the most striking discrepancies between theory and observation in modern physics. Regardless of its true nature, for dark energy to accelerate cosmic expansion, it must generate a profoundly negative pressure. In the equations of general relativity, pressure contributes to gravitational effects just as mass does. This negative pressure counters gravity, pushing the fabric of space outward, a phenomenon sometimes referred to as gravitational repulsion. If the universe were instead contracting, the same effect would slow the contraction. Breaking the universe into its fundamental components reveals three categories: matter, radiation, and dark energy. Matter encompasses all particles with mass, from colossal stars to microscopic dust grains. As space expands, the energy density of matter diminishes in proportion to the cube of the expansion factor. Radiation, including light and heat, behaves slightly differently. Its energy diminishes faster than matter because, in addition to spreading out, its wavelengths stretch, a process called redshift. Dark energy, however, behaves in an entirely unique manner. Its density remains constant as the universe expands, filling the ever-growing void and driving cosmic acceleration continuously. Multiple lines of evidence support dark energy's existence. Observations of distant galaxies and supernovae reveal that light reaching Earth has been stretched over time, indicating the universe's expansion is accelerating. The shape of the universe appears flat, meaning total energy must meet a precise threshold. Matter alone cannot account for this balance, necessitating a pervasive energy component. Patterns in the distribution of galaxies also hint at dark energy's influence, revealing large-scale structures that could not have formed without its presence. In 1998, the High-Z supernova search team made a groundbreaking discovery while studying Type 1a supernovae. Contrary to expectations that cosmic expansion would be slowing under gravity, they found it accelerating. A year later, the Supernova Cosmology Project confirmed the finding. Their work reshaped our understanding of the cosmos and earned the Nobel Prize in Physics in 2011. Since then, observations of the cosmic microwave background, remnants of the Big Bang itself, have provided additional compelling evidence supporting the profound, invisible force known as dark energy. Additionally, astronomers have devoted decades to studying the subtle ways that light behaves when it passes near massive objects in space, a phenomenon known as gravitational lensing. As light bends and warps around galaxies, clusters, and other cosmic giants, it creates a natural magnifying effect, revealing hidden details about distant parts of the universe. Alongside this, scientists have painstakingly mapped the large-scale structure of the cosmos, tracing the intricate cosmic web of galaxies, filaments, and voids that stretches across unimaginable distances. These observations have converged on a startling conclusion. A mysterious, invisible force known as dark energy is driving the universe's expansion at an ever-increasing rate. While some skeptics point out that the clearest evidence comes from measuring redshift, the way light stretches as galaxies recede, and the distances of supernovae, this is far from the whole story. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, reveal subtle patterns that also point to accelerated expansion. Supernovae are particularly invaluable for this research because they serve as cosmic measuring sticks, often referred to as standard candles. The brilliance of these stellar explosions is remarkably consistent, allowing astronomers to determine their distances with high precision. By By comparing these distances with the degree to which their light has stretched, scientists can chart the universe's expansion across time. Type 1a supernovae are especially critical because they explode with a nearly uniform luminosity, providing some of the most reliable markers in the cosmos. Recent measurements suggest that dark energy constitutes roughly 71% of the total energy content of the universe, with the remaining 29% comprised of dark matter and ordinary matter. The prevailing theories of cosmic structure formation indicate that matter alone accounts for only about 30% of the critical density necessary for a geometrically flat universe. Additional support for dark energy came from the Wiggle-Z Galaxy Survey in 2011, which analyzed more than 200,000 galaxies, some located as far as 2 billion parsecs away. Innovative techniques allowed researchers to measure these vast distances with remarkable precision, further confirming that the universe's expansion is accelerating. For the universe to appear as flat as it does, there must exist a form of energy that fills the voids between galaxies. Observations indicate that all observable matter, whether ordinary or dark, accounts for only 30% of what is required. The remaining 70% is attributed to dark energy. Data from the Wilkinson Microwave Anisotropy Probe, which mapped the early universe in unprecedented detail, estimated dark energy's contribution at around 73%. More recent results from the Planck satellite refined this estimate, indicating that dark energy makes up about 68%, dark matter around 27%, and ordinary matter just under 5%. Dark energy also provides explanations for the subtle temperature fluctuations observed in the cosmic microwave background. As photons travel through regions of strong gravitational influence, such as clusters of galaxies or vast cosmic voids, they gain or lose energy, creating tiny variations in the background radiation. This phenomenon, known as the integrated Sachs-Wolf effect, offers another significant clue to dark energy's presence. Scientists have developed additional methods to probe dark energy by measuring the Hubble constant, which describes the rate of cosmic expansion over time. By studying galaxies that have evolved predictably and treating them as cosmic clocks, researchers analyze their ages and redshifts to estimate how the expansion rate has changed throughout the universe's history. Despite mounting evidence, dark energy remains one of the greatest mysteries in physics. Researchers universally agree that it drives the accelerating expansion of the cosmos, yet its fundamental nature remains unknown. Various approaches are being explored. Some scientists revisit Einstein's theory of gravity to determine if modifications are required, while others attempt to characterize dark energy's properties or investigate alternative explanations prompted by unexpected cosmic observations. One of the simplest theories posits that dark energy is an intrinsic feature of space itself. According to this view, even empty space contains a baseline energy called vacuum energy, represented in the cosmological constant and symbolized by the Greek letter lambda. This principle underpins the lambda CDM model, the most widely accepted framework for understanding cosmic evolution. Einstein's famous equation equates mass and energy, suggesting that vacuum energy exerts a gravitational influence, subtly driving the universe's expansion. Yet this theory faces a profound challenge. Quantum physics predicts a vacuum energy density roughly 120 orders of magnitude higher than observed. If this were accurate, the universe would have expanded so violently that stars, galaxies, and planets could never have formed. Instead, we observe a universe rich with complex structures that have evolved over billions of years, implying that most of this energy is somehow balanced without being entirely canceled, a mystery that continues to baffle physicists. While many theories treat dark energy as a constant force, some researchers propose a more dynamic entity, an evolving energy field known as quintessence. Unlike the cosmological constant, quintessence changes over space and time, influencing the universe's expansion differently in various epochs. It is thought to be extremely light, preventing it from clumping together like ordinary matter. Some quintessence models suggest that the universe's expansion is slightly slower than predicted by the standard model, though definitive proof remains elusive. A particularly perplexing question is why dark energy has become dominant at this point in cosmic history. If it had emerged too early, the universe's rapid expansion might have inhibited galaxy formation, precluding the development of life as we know it. Some scientists argue this is coincidental, while others invoke the anthropic principle, which asserts that the universe must be compatible with the observers within it. Certain quintessence models incorporate a tracker mechanism that naturally explains dark energy's timing, linking its influence to the density of radiation in the early universe. These models account for the delayed but dramatic emergence of cosmic acceleration. More extreme versions of quintessence predict even stranger outcomes, hinting at a universe that may evolve in ways far beyond our current understanding, leaving the true nature of dark energy as one of the most profound enigmas in science. One of these possibilities is phantom energy, a peculiar and enigmatic form of dark energy that defies intuition by growing stronger over time rather than remaining constant. If this concept holds true, the universe's expansion would not merely continue indefinitely, it would accelerate toward a cataclysmic finale known as the Big Rip. In this nightmarish scenario, the force driving the universe's expansion would intensify to unimaginable levels, sequentially ripping apart galaxies, tearing stars asunder, shattering planets, and ultimately disassembling atoms themselves, reducing all matter to an absolute void. Another intriguing variant of dark energy, referred to as K-essence, proposes that the universe could be permeated by exotic forms of energy, exhibiting behaviors entirely foreign to our experience. Some formulations of K-essence even allow for the existence of negative kinetic energy, introducing the possibility of bizarre, unpredictable consequences for the universe's evolution. Recent observations have highlighted inconsistencies in the measurements of cosmic expansion, a discrepancy termed the Hubble tension. This mismatch suggests that our standard model of cosmology may be missing critical pieces of the puzzle. Researchers speculate that only certain models of quintessence equipped with additional interactions might resolve this anomaly. Despite decades of investigation, dark energy remains one of the most profound mysteries in modern physics. Yet it is intimately linked to Albert Einstein's theory of general relativity. Some theorists argue that modifying general relativity in specific ways could eliminate the need for dark energy entirely, though none of the proposed alternative theories have been definitively validated. The groundbreaking detection of gravitational waves from the event GW17100817 has already invalidated many of these modified gravity hypotheses. According to astrophysicist Ethan Siegel, while sensational alternative theories capture headlines, the majority of experts continue to support the reality of dark energy as competing frameworks fail to align with observational data as accurately as the prevailing model. Current estimates indicate that the universe's accelerated expansion began approximately 5 billion years ago. Prior to that epoch, gravitational forces from both dark matter and ordinary matter dominated, slowing the cosmic expansion. As the universe expanded, matter became increasingly diffuse, diminishing its influence, while dark energy remained nearly constant. Eventually, this persistent dark energy prevailed, driving the universe into an era of accelerated expansion. For every instance that the universe doubles in size, the concentration of dark matter in any given volume is halved. Yet the density of dark energy remains almost unchanged. The ultimate fate of the cosmos hinges on the true nature of dark energy. If it remains constant, as the cosmological constant model suggests, the universe will continue expanding indefinitely. Over vast spans of time, galaxies will recede from one another at speeds exceeding that of light, not by moving through space, but because space itself is stretching. Presently, the cosmological event horizon, the distance beyond which no information can ever reach us, is roughly 16 billion light years. Events occurring within this boundary may eventually be observed, but anything beyond it is lost to us forever. As galaxies drift toward this horizon, their emitted light is stretched into ever longer wavelengths, gradually vanishing from sight. To a distant observer in the far future, galaxies outside our local group would fade into oblivion, leaving a solitary cluster in an otherwise empty expanse. While the vision of a perpetually expanding dark and desolate universe is chilling, other scenarios are even more extreme. If dark energy intensifies over time, the universe could succumb to a big rip, obliterating all matter and energy. Alternatively, if dark energy diminishes or reverses, cosmic expansion could halt, followed by a catastrophic contraction known as the Big Crunch, ultimately collapsing the cosmos back into a singular point and potentially igniting another Big Bang. Some models even propose a cyclic universe, where expansion and contraction repeat endlessly in a cosmic rhythm of creation and destruction. Closely intertwined with these cosmic mysteries is the anthropic principle, a concept suggesting that the universe must possess conditions suitable for life, simply because observers exist to notice them. This principle implies that the universe appears finely tuned for life, not due to design, but because only a life-permitting universe allows conscious beings to arise. Proponents argue that the anthropic principle helps explain why the universe has its particular age and physical constants, as even slight deviations could have prevented intelligent life from emerging. For instance, a younger universe would not have allowed stars sufficient time to produce the heavier elements necessary for planets and life. Conversely, an older universe might have exhausted most stars, leaving planetary systems like ours improbable. The fundamental constants governing physics, from the strength of the nuclear forces to the gravitational constant, seem precisely calibrated to allow life. Even minor variations in these numbers could radically alter the formation of elements, planetary systems, and the conditions necessary for life. The term anthropic principle was first coined by theoretical physicist Brandon Carter during a 1973 conference commemorating the 500th birthday of Copernicus. Carter introduced it as a counterpoint to the Copernican principle, which asserts that humans do not occupy a special or central location in the cosmos. While human beings may not be at the center, Carter argued the conditions we observe are nevertheless privileged, allowing intelligent life to exist. He outlined two versions: the weak anthropic principle, stating that humans exist in specific regions and times because those conditions permit life, and the strong anthropic principle, proposing that the universe's fundamental constants may be intrinsically structured to support life. This latter concept raises profound questions, given that we inhabit only one known universe with fixed laws. Carter suggested two potential explanations. Either humans can deduce the values of physical constants because they exist within this universe, or there may be countless universes, each with distinct laws of physics, with ours being one among the rare life-supporting few, a precursor to what is now known as the multiverse theory. Over time, the anthropic principle has evolved, especially after John D. Barrow and Frank Tipler expanded and redefined its weak and strong versions in 1986, creating new interpretations and sparking debate within the scientific community. The principle continues to provoke reflection on the delicate balance of forces, the precise tuning of cosmic parameters, and the mysterious alignment of conditions that make life possible, revealing the profound intricacies and astonishing coincidences embedded in the fabric of the cosmos. However, Carter was far from the first to explore these profound questions about the universe and our place within it. As early as the year 1904, the evolutionary biologist Alfred Russel Wallace proposed that the staggering vastness and intricate complexity of the cosmos might not be arbitrary, but rather necessary to create conditions suitable for human life. Decades later, in 1957, the physicist Robert Dicke emphasized that the universe's age and timing are far from coincidental. He argued that biological factors dictate why intelligent beings like humans emerge precisely at this particular epoch in cosmic history. Dicke also pointed out that even the slightest variation in the fundamental constants of physics would have prevented human existence altogether, leaving these existential questions forever unasked. Yet the curiosity over such cosmic coincidences stretches back even further. In the late 19th century, the Austrian physicist Ludwig Boltzmann wrestled with the universe's seemingly low entropy, a measure of disorder, which appeared at odds with the chaotic tendencies predicted by thermodynamic laws. Boltzmann speculated that random fluctuations could produce fleeting pockets of order, isolated regions where the natural tendency toward chaos temporarily gives way to structure. Intelligent life, he argued, exists precisely in one of these rare, orderly regions because such conditions are the only ones capable of supporting it. Carter's formulation of the anthropic principle, though conceptually straightforward, sparked intense debate, largely because its elegance masks a subtle complexity. The observation is simple. The universe appears finely tuned for life, so perhaps it is. Influential scientists such as Stephen Hawking and Michael Collins considered that this apparent fine-tuning might arise from a vast multiplicity of universes, each with its own unique initial conditions. In such a scenario, most universes would be inhospitable, but in an infinite multiverse, some, including ours, would inevitably foster life. While philosophical reflection on these ideas stretches back centuries, by the early 1970s, the only scientific framework capable of accommodating multiple universes was the many worlds interpretation of quantum mechanics, which posits that every quantum event spawns branching timelines. However, this interpretation does not permit variations in the fundamental constants of physics, leaving a crucial question unresolved. During the 1980s, theoretical breakthroughs provided new insight. Inflation theory, combined with symmetry breaking in the early universe, offered a plausible mechanism through which physical constants could vary across distinct regions of space. By the early 21st century, string theory expanded this possibility dramatically. It raised the question of whether every fundamental constant, including the very number of spatial dimensions, could vary across an unimaginably vast landscape of potential universes. This challenged the traditional physicist's ambition of discovering a single, all-encompassing theory of everything with no free parameters. Albert Einstein himself once wondered whether God had any choice in establishing the laws of physics, essentially asking whether the universe is compelled to be the way it is, or whether it could have been otherwise. By 2002, string theorists believed they were approaching a framework that might eliminate the need for the anthropic principle entirely. Yet, just a year later, Leonard Susskind contended that the vast complexity of the string landscape made the anthropic principle more plausible than ever, suggesting that the apparent fine-tuning of our universe could be a natural consequence of its place among countless alternatives. This principle also intersects with debates about intelligent design. Advocates of intelligent design cite fine-tuning as evidence for a creator, while critics counter that apparent fine-tuning might not be as remarkable as it seems. Some argue that even if fine-tuning exists, it does not necessarily indicate an intelligent designer. Others maintain that the anthropic principle itself undercuts arguments for intelligent design by offering a naturalistic explanation for why the universe supports life. Carter distinguished between the weak and strong forms of the anthropic principle. The weak version serves as a guiding principle rather than a testable hypothesis, suggesting that the universe must be compatible with the conscious life observing it. The strong version posits that the universe is in some sense required to support life, a proposition that would demand evidence of life beyond our own universe, a daunting, if not impossible, task given observational constraints. Philosopher John Leslie leveraged the strong anthropic principle to predict that the laws of physics are shaped by chance rather than rigid necessity, hinting that the universe's precise conditions are contingent rather than predetermined. Evidence for fine-tuning continues to accumulate. Mathematical studies of galaxy formation confirm that the universe's expansion rate critically shapes cosmic structures, while researchers like Craig Hogan argue that if all fundamental constants were strictly fixed, there would be no explanatory framework for their life-permitting values. In this view, humans are compelled to confront the extraordinary improbability of our existence, accepting that the universe seems tailored to permit life. Astronomer Fred Hoyle exemplified anthropic reasoning in action. Observing that life on Earth depends on carbon, particularly carbon-12, he predicted the existence of a previously unknown resonance within stars that would facilitate its production through the triple alpha process. His calculations indicated that this resonance should exist at roughly 7,600,000 electron volts, a prediction confirmed shortly thereafter by Willie Fowler and his team, whose measurements closely aligned with Hoyle's forecast. Yet the historical narrative of anthropic reasoning is more nuanced. In 2010, historian Helga Krag argued that Hoyle did not employ anthropic reasoning in 1953. She claimed that the concept of the universe appearing fine-tuned for life did not gain traction until 1980, and suggested that scientists only recognized the connection between carbon and life after the resonance had been discovered, coining the term anthropic myth. Another area of intense discussion involves cosmic inflation, which describes the universe's rapid early expansion. Don Page criticized inflationary theory, highlighting the improbability of the universe's extremely low initial entropy, an essential prerequisite for the forward flow of time. Paul Davies countered, arguing that an inflationary anthropic principle resolves this issue, positing that the universe began as a small, highly ordered patch that expanded into the cosmos we observe today, thereby reinforcing the inflationary model without additional assumptions required by other Big Bang theories. String theory adds another layer of complexity by proposing that a staggering number of possible universes, or vacua, populate what is known as the multiverse, or the string landscape. Leonard Susskind contended that anthropic reasoning becomes almost inevitable in this context. We exist only in the subset of universes with life-supporting conditions, while the rest remain forever unobserved. Steven Weinberg regarded this as a pivotal shift, allowing cosmologists to account for the universe's finely tuned constants without invoking divine intervention. Critics, including David Gross, Lubos Model, Peter Voigt, and Lee Smolin, argued that anthropic explanations fail to yield concrete predictions. At the same time, researchers such as Max Tegmark, Mario Livio, and Martin Rees emphasized that many accepted scientific theories remain untestable in full, yet retain their validity. Between 2000 and 2002, Jürgen Schmidhuber highlighted an alternative perspective, referencing Ray Solomonoff's theory of universal inductive inference as a method for logically assessing scientific theories based on limited data. Schmidhuber argued that this approach provides the most rigorous way to evaluate reliability, even when direct testing is impossible. Researchers Shihui Wang and Samuel L. Brownstein examined the dependence of life on certain fundamental physical constants, cautioning that incomplete understanding might lead to the mistaken conclusion that the universe was intentionally designed for life. Their findings suggest that other universes with different constants could also support life, challenging the notion that our universe is uniquely special. The intricate interplay of physics, cosmology, and philosophy continues to shape our understanding of why the universe allows life to emerge, revealing a web of possibilities that stretches from the earliest moments of cosmic history to the unfathomable reaches of the multiverse. The conversation evolves with every theoretical breakthrough, each observation, and each bold prediction, illustrating the delicate balance between chance, necessity, and the profound mystery of existence itself.